Imagine standing at the edge of a cliff on a moonless night. You cannot see the ground below, but you can feel the pull. Something massive waits in that darkness, patient and absolute. Now multiply that sensation by a factor so large it loses all meaning to the human mind. Multiply the cliff by 10,000 galaxies. Multiply the darkness by 50 million light years, and understand that you're not standing at the edge of this void, you are falling into it. You have been falling since before the Earth existed. You will continue falling long after the sun burns to ash. And the most terrifying part, the detail that should keep cosmologists awake at night, is that you cannot even see what is pulling you. It hides behind a curtain of stars, dust and light, our own galaxy's body obscuring the very thing that commands its destiny. This is the Great Attractor. This is the invisible hand shaping the motion of everything we have ever known. And we discovered it almost by accident, through careful measurements that revealed something profoundly wrong with our assumptions about the universe. To understand the Great Attractor, we must first understand what it means for galaxies to move, not to drift, not to wander, but to be compelled. In the everyday physics of our terrestrial experience, objects move because forces act upon them. A ball rolls because a hand pushed it. A river flows because gravity draws water toward the sea. But galaxies operate on scales that dwarf these familiar mechanics. A single galaxy contains hundreds of billions of stars, each one a furnace of nuclear fire. The Milky Way spans 100,000 light-years from edge to edge. To move such an object, to actually accelerate it in a given direction, requires forces that exceed human comprehension by orders of magnitude. And yet, galaxies move. They don't merely rotate in place or expand with the general flow of space-time. They have peculiar velocities, motions that deviate from the pure expansion of the universe, movements toward or away from other concentrations of matter. For decades, astronomers assumed these peculiar velocities would average out across large enough samples. Galaxies might stream toward one cluster here, away from another there, but the universe should look roughly the same in all directions. This is called isotropy, the cosmological assumption that no direction in space is fundamentally special. What astronomers found instead was a flow, a river of galaxies, an entire quadrant of the observable universe sliding toward a single invisible point. The year was 1976 when the first hints emerged. Two astronomers, Vera Rubin and Kent Ford, had been studying the rotation curves of spiral galaxies, work that would eventually lead to the discovery of dark matter. But in the process of their observations, they noticed something peculiar in the data. Galaxies weren't quite where they should be. Their redshifts, the stretching of light that tells us how fast they're moving away from us, showed small but consistent deviations from pure expansion. Some galaxies were approaching faster than expected. Others were receding slower. The pattern wasn't random. At first they hesitated to publish. The deviations were small, and cosmology in the 1970s was still wrestling with fundamental questions about the nature of the universe itself. The cosmic microwave background had been discovered only a decade earlier. Dark matter remained controversial. Dark energy was utterly unknown. To claim that galaxies were streaming toward an unseen point would have been extraordinary, and extraordinary claims required extraordinary evidence, but the data persisted. Other researchers, using different methods and different telescopes, began to see the same signature. The peculiar velocities of galaxies weren't averaging out. They were coherent, aligned. Something was pulling. By 1986, a team of astronomers known as the Seven Samurai had amassed enough evidence to make the claim undeniable. Alan Dressler, Sandra Faber, Donald Lyndon Bell and their colleagues had measured the distances and velocities of hundreds of elliptical galaxies. They used a relationship called the Faber-Jackson correlation, which connects a galaxy's luminosity to its internal stellar velocities. By comparing how bright a galaxy appeared to how bright it should be at a given distance, they could calculate how far away it actually was. And by comparing that distance to its redshift, they could determine its peculiar velocity, the motion that couldn't be explained by simple expansion. What they found stunned the astronomical community. Galaxies within a volume spanning hundreds of millions of light-years were all moving in roughly the same direction. Not slightly, dramatically. The Milky Way itself was racing toward the constellation Centaurus at approximately 600 kilometers per second, relative to the cosmic microwave background. That's 1.3 million miles per hour. Fast enough to cross the entire diameter of the Moon in 12 seconds. Fast enough to reach Alpha Centauri, our nearest stellar neighbour, in roughly 2,000 years. And we weren't alone. The Andromeda Galaxy was falling with us. The entire local group, the gravitational collective that includes the Milky Way, Andromeda, the Triangulum Galaxy, and dozens of dwarf galaxies, was streaming in the same direction. So was the Virgo cluster, the nearest large collection of galaxies, some 50 million light-years away. The entire Laniakea supercluster, a structure containing 100,000 galaxies spanning 500 million light-years, was participating in this cosmic flow. All of it moving toward a point we could not see. The Seven Samurai called it the Great Attractor, a name both evocative and deliberately vague. They knew something massive had to be generating this flow. Gravity is the only force that operates at such scales, and gravity requires mass. But how much mass? Their calculations suggested a concentration equivalent to tens of thousands of Milky Way galaxies, all packed into a relatively small region of space. This was not merely a cluster. This was something larger, something more fundamental to the architecture of the cosmos. But here is where the story takes its most unsettling turn. The direction of this flow, the point toward which all these galaxies are falling, lies almost precisely behind the disk of our own Milky Way. Astronomers call this region the zone of avoidance. It is a band of sky, roughly 20 degrees wide, where the dense stars, gas and dust of our galactic plane block optical light from distant objects. Imagine trying to see across a crowded stadium while someone holds a spotlight directly in your eyes. The glare of our own galaxy blinds us to whatever lies beyond. We are being pulled toward a destination we cannot observe. The universe's largest local structure remains hidden from direct view by the cosmic accident of our position within our own galaxy. This is not malevolent design. The universe has no intentions, but the effect is the same. We are blind to our own fate. For years, astronomers could only infer the Great Attractor's properties from its effects. They could measure the flow. They could calculate the required mass. They could narrow down the direction to a patch of sky in the southern constellation Centaurus, roughly 250 million light-years away. But they could not see what was there. Optical telescopes were useless. The zone of avoidance swallowed every photon of visible light. The breakthrough came from a different kind of vision entirely. In the 1990s, astronomers began surveying the hidden sky using infrared light and radio waves, frequencies that could penetrate the dust and gas obscuring the Milky Way's disk. These observations revealed a landscape far richer and more complex than anyone had imagined. Behind the curtain of stars they found galaxies, thousands of them, tens of thousands. The zone of avoidance was not empty. It had merely been invisible, and at the heart of the region toward which everything was flowing, they discovered a massive structure that had been hiding in plain sight, or rather, hiding in plain darkness. It was called the Norma Cluster, also known as Abell 3627, a rich concentration of galaxies, containing hundreds of members, anchored by a massive elliptical galaxy at its centre. The Norma Cluster was large, one of the most massive galaxy clusters within a few 100 million light-years of Earth, but it wasn't large enough. Its mass could account for perhaps a quarter of the gravitational pull required to explain the observed flow. Something else had to be contributing. The Great Attractor was not a single object, but a convergence of many massive structures, a gravitational well created by the superposition of multiple clusters, superclusters, and vast filaments of dark matter. This realization transformed the Great Attractor from a point into a region, from a destination into a landscape. It wasn't a cosmic drain pulling galaxies toward a single spot. It was a basin, a depression in the fabric of space-time created by an enormous concentration of mass distributed across millions of light-years, and our galaxy, along with everything around us, was rolling downhill. Picture a rubber sheet stretched taut across a frame. Now place a bowling ball in the centre. The sheet deforms, creating a valley, and any marbles placed on the sheet will roll toward the ball. This is the standard analogy for gravity in general relativity. Mass curves space-time, and objects follow those curves. Now imagine that bowling ball is actually a collection of many heavy objects spread across the sheet. The valley is broader, shallower, more complex. There are local depressions within the larger basin. Some marbles fall toward local weights before continuing toward the deeper centre. the motion becomes a flow, a river system with tributaries and branches. This is what astronomers now understand the Great Attractor region to be. The Norma cluster is one massive object in the basin. The Centaurus cluster is another, closer to us, contributing its own gravitational influence. The Hydra cluster adds its mass. The Shapley supercluster, even farther beyond the Great Attractor at 700 million light-years, pulls everything toward an even deeper centre. The entire structure forms a cosmic hierarchy, wheels within wheels, flows within flows, all directed toward ever larger concentrations of matter. And yet, even this expanded understanding brings its own disquiet. Because the discovery of ever larger structures beyond the Great Attractor raised a troubling question. Where does it end? How deep does the cosmic hierarchy go? And what does it mean for our understanding of the universe if matter is clumped so dramatically on such enormous scales? Cosmology in the 20th century was built on the assumption that the universe, on sufficiently large scales, should be homogeneous. The cosmic microwave background, that faint afterglow of the Big Bang, is remarkably uniform. It varies by only 1 part in 100,000 across the entire sky. This uniformity suggested that the universe should look roughly the same everywhere, at least when you zoom out far enough. Galaxies might cluster locally, but the clusters should be distributed randomly, with no preferred directions or destinations. The Great Attractor challenged this assumption. The flows it generated stretched across hundreds of millions of light-years. The structures contributing to it spanned a significant fraction of the observable universe. If such vast coherent motions existed, was the universe really as homogeneous as cosmologists believed? Or were we simply too small, too embedded in local flows to perceive the true architecture of reality? The answer, it turned out, was both reassuring and humbling. Yes, the universe is homogeneous, on truly cosmic scales. At distances of billions of light-years, the distribution of matter does become remarkably uniform. But our local region, the patch of space we call home, is anything but uniform. We live in a structured universe, a universe of walls and voids, filaments and nodes, rivers and basins. The Great Attractor is not an anomaly. It is a feature. One of many, a single convergence point in a cosmic web that spans the observable universe. This web was first glimpsed in the 1980s when astronomers began mapping the three-dimensional distribution of galaxies using redshift surveys. What they found defied the smooth uniformity they expected. Galaxies weren't scattered randomly like points in a featureless fog. They were arranged in structures. Long, thin filaments connected dense clusters. Between the filaments lay enormous voids, bubbles of empty space spanning hundreds of millions of light-years. The universe looked less like a gas and more like a sponge, a foam, a network of luminous threads surrounding hollow cavities. The first great void was discovered in 1981 in the direction of the constellation Boötes. It measured 300 million light-years across, a gulf of near emptiness containing almost no galaxies at all. Other voids followed, each one challenging the assumption that matter should be distributed smoothly. And with each new survey, the filaments connecting these voids grew more intricate, more connected, more evidently part of a single vast structure. This is the cosmic web, and the Great Attractor is one of its densest nodes, a place where multiple filaments converge, where matter has been gathering since the universe was young, where gravity has slowly drawn galaxies into an ever tighter embrace. Our own galaxy is embedded in this web, sliding along a filament toward the nearest concentration of mass. We are not falling through empty space. We are flowing along the contours of a structure larger than we can imagine. The numbers defy intuition. The Laniakea supercluster, the structure of which the Milky Way is a part, contains roughly 100,000 trillion solar masses. That's a 1 followed by 17 zeros. It spans 500 million light-years, a distance so vast that light takes 500 million years to cross it. And yet Laniakea is just one supercluster among many. The Shapley supercluster, which lies beyond the Great Attractor, is even more massive. The Sloan Great Wall, discovered in 2003, stretches 1.4 billion light-years. The Hercules Corona Borealis Great Wall, announced in 2014, may span 10 billion light-years, a structure so large it challenges our understanding of how such things could form in the available time since the Big Bang. We live in a universe of monsters, structures so vast they dwarf galaxies the way galaxies dwarf planets, and all of them are moving, flowing, falling toward the densest concentrations of matter, driven by the patient, relentless pull of gravity. The Great Attractor is one such concentration. Not the largest, not the final destination, but a waypoint on a longer journey. Current research suggests that the Laniakea supercluster, including the Milky Way, is itself falling toward the Shapley concentration, a supercluster of superclusters lying some 650 million light-years away in the direction of the Centaurus Hydra region. The Shapley concentration contains roughly 8,000 galaxies and exerts a gravitational pull that may eventually merge with the Great Attractor's influence, creating an even larger basin of attraction. And beyond Shapley, the flow continues. Some astronomers now speak of a dipole repeller, a vast void in the opposite direction from the Great Attractor that may be pushing us as much as the attractor pulls. The dynamics of large-scale structure involve not only falling toward dense regions, but fleeing from empty ones. We are caught between giants, squeezed by absence and presence alike. This is the architecture of the universe as we now understand it. Not a smooth expansion from a single point, but a turbulent ocean of flows and counterflows, attractions and repulsions, matter gathering into ever larger structures while space itself stretches between them. The cosmic microwave background may be smooth, but the galaxies that formed from its tiny fluctuations have organized themselves into a web of stunning complexity. And we are embedded in that web, carried by currents we cannot control toward destinations we cannot see. The invisibility of the Great Attractor adds a layer of cosmic irony to this situation. Of all the places in the sky where such a massive structure might lie, it happens to be hidden behind the very galaxy that harbours the only beings, as far as we know, capable of understanding it. If the Great Attractor were located 60 degrees further from the galactic plane, we would have photographed it decades ago. We would have pretty pictures, detailed surveys, precise measurements. Instead, we must peer through the thickest part of our own stellar disk, using wavelengths that most telescopes were not designed to detect, reconstructing the shape of something we cannot directly see. This is not a metaphor for the human condition, but it might as well be. We are creatures who evolved to navigate a small world, to track prey across savannas, to recognize faces and detect threats. Our brains are wired for the immediate, the tangible, the visible. And yet we have somehow managed to discover that we are falling through intergalactic space toward an invisible mass concentration 250 million light-years away, carried by forces that have been operating since before our planet formed, destined for a collision we cannot prevent on timescales that make human history vanish into insignificance. The Great Attractor will never reach us in any meaningful sense. We will reach it, or rather our region of space will eventually merge with its gravitational influence, falling deeper into the basin that already holds us. But this process unfolds over billions of years. The universe expands even as galaxies flow toward local attractors, and the rate of expansion is accelerating. Dark energy, that mysterious repulsive force pervading all of space, pushes the universe apart faster than gravity can pull it together. In the distant future, perhaps 50 billion years hence, the cosmic web may tear itself apart. Superclusters will separate. Filaments will stretch and fade. Individual galaxy groups will become isolated islands, forever cut off from their neighbours by the growing gulfs of expanding space. But for now, for the next few billion years, the flow continues. The Milky Way falls toward the Great Attractor. The Great Attractor falls toward Shapley. Shapley may fall toward something even larger, some ultimate concentration that anchors the flow of a billion galaxies. We are part of a cosmic river system, tributaries joining streams, joining rivers, joining an ocean that may have no shore. What would it look like to actually visit the Great Attractor region? To somehow travel 250 million light-years and witness the structures that pull us onward? The journey itself would be impossible by any known physics. The distances involved exceed what light can cross in a human lifetime by factors of millions. But imagine for a moment that you could make the trip. You would leave the Milky Way, passing first through the local group, that modest collection of galaxies bound together by gravity. Andromeda would dominate your view, a spiral galaxy larger than our own, surrounded by its retinue of dwarf companions. Beyond the local group you would enter the local void, a relatively empty region that separates us from the nearest major cluster. Space here is not truly empty. Lone galaxies drift through the darkness, isolated from their neighbours, but the contrast with the structure ahead would be stark. As you approach the Virgo cluster, 50 million light-years from Earth, you would enter the first truly dense environment on your journey. Virgo contains roughly 2,000 galaxies, a great metropolitan hub of the cosmic web. Giant elliptical galaxies dominate its centre, their surfaces smooth and ancient, their stars orbiting in random swarms rather than organised disks. These are the oldest structures in the universe, formed from the merger of dozens of smaller galaxies over billions of years. Their mass anchors the cluster, drawing in smaller members, warping space-time into a local depression in the larger basin that leads to the Great Attractor. But Virgo is only a waypoint. The flow continues. You would pass through the Centaurus cluster, 130 million light-years from Earth, another concentration of hundreds of galaxies, then onward, deeper into the zone of avoidance, where the stars of the Milky Way would no longer obstruct your view, because you would have left them far behind. The dust and gas that blinds Earth-based telescopes would be irrelevant from this vantage point. You would see what we cannot see, the heart of the attractor itself. And what would you find? Not a single massive object, not a cosmic drain or a black hole the size of a galaxy. You would find structure. Clusters upon clusters, connected by filaments of galaxies and dark matter. The Norma cluster would anchor one region, its thousands of member galaxies orbiting a common centre. Other clusters would spread across millions of light-years, each one a gravitational well contributing to the overall pull. The Shapley concentration would loom beyond, even more massive, its influence reaching back across hundreds of millions of light-years to tug at the very galaxies you left behind. The Great Attractor, from this imagined vantage point, would resolve from a single point into a landscape, a gravitational terrain, with peaks and valleys, ridges and basins. You would understand that the flow is not toward a destination but through a topology, a region of curved space-time where all paths lead inward. The galaxies caught in this flow are not falling towards something so much as they are following the shape of space itself, rolling along geodesics carved by the distribution of matter on cosmic scales. This is the universe as gravity has built it. Not the smooth, uniform cosmos of early models, but a textured, structured realm where matter clumps and flows, where great rivers of galaxies pour toward concentrations of mass that have been growing since the first moments after the Big Bang. The seeds of this structure were planted in the primordial plasma, tiny fluctuations in density that inflation stretched to cosmic scales. Those fluctuations grew over billions of years, attracting matter, merging, collapsing, forming the web we observe today. The Great Attractor is one node in that web, a particularly dense node, a particularly strong influence on our local cosmic environment, but it is not unique. Every supercluster has its attractor, its gravitational centre, its basin of flow. The universe is full of such structures, each one drawing in the galaxies around it, each one participating in the grand dance of matter and gravity that has been playing out since the beginning of time. And yet, despite the universality of such structures, the Great Attractor holds a special place in our imagination. It is the one we cannot see. It is the one that pulls us specifically toward a fate we did not choose and cannot control. There is something almost mythological about it. A hidden power, a destination veiled from view, a force that shapes our cosmic journey, while remaining forever obscured. Perhaps this is why the name has endured. Great Attractor. Not a Bell 3627, not the Norma supercluster. Great Attractor, with all its connotations of vastness and inevitability and unseen influence. It sounds like something from ancient cosmology, a name for a god or a force of nature, something that commands worship or fear, and in a sense it deserves that awe. The Great Attractor is not alive, not conscious, not capable of intention, but it is real, and it is powerful, and it is pulling us toward it right now, as you listen to these words, at a speed that would carry you from New York to Los Angeles in 4 seconds. We are falling. We have always been falling, and the darkness that hides our destination only deepens the mystery. The astronomers who first discovered the Great Attractor could not have known how completely it would reshape our understanding of the universe. They were looking for peculiar velocities, deviations from smooth expansion, evidence that galaxies moved in response to local mass concentrations. What they found was a flow that stretched across a significant fraction of the observable universe, a coherent motion involving hundreds of thousands of galaxies, a structure that challenged the assumptions of cosmological homogeneity that had guided the field for decades. In the years since that discovery, our maps of the cosmic web have grown ever more detailed. We have surveyed millions of galaxies, measured their distances and velocities, traced the filaments and voids that shape their distribution. We have discovered that the Milky Way is part of a supercluster called Laniakea, a name drawn from Hawaiian words meaning immense heaven. We have traced the boundaries of that supercluster, identified its flow patterns, understood its relationship to the larger structures beyond. And at the heart of it all, still partially hidden behind our galaxy's disk, lies the region we call the Great Attractor. The mystery has not been solved so much as deepened. Every answer has raised new questions. Every map has revealed more structure, more flows, more evidence that the universe is not the simple, uniform place we once imagined. And the Great Attractor remains at the centre of our local cosmic drama, the gravitational anchor that will continue to shape the motion of our galaxy for billions of years to come. What happens next, in the long span of cosmic time? The Milky Way will continue falling toward the attractor, though it will never truly arrive. The basin is not a destination, but a feature of space-time, and the galaxies caught within it will eventually merge, collide, combine into ever larger structures. In 4 to 5 billion years, the Milky Way will collide with Andromeda, a merger that will reshape both galaxies into a single giant elliptical. That merged galaxy, sometimes called Milkomeda, will continue falling toward the attractor, continuing the flow that began when both galaxies first formed. On longer timescales, the expansion of the universe will change the game entirely. Dark energy will stretch space faster than gravity can contract it. The cosmic web will thin and fade. Superclusters will pull apart, clusters will isolate, and eventually each galaxy group will become a lonely island in an expanding void. The Great Attractor will cease to attract because there will be nothing left to pull. The flow will stop. The river will dry up, but that end lies trillions of years in the future. For now, the flow continues. The Great Attractor waits in the darkness hidden behind the stars of our own galaxy, pulling us onward toward a destiny we cannot see. And we, the brief conscious flickers in this vast cosmic machinery, have somehow managed to detect its presence, to measure its influence, to name the invisible force that shapes our galactic fate. That, perhaps, is the most remarkable part of this story. Not the attractor itself, which is merely matter doing what matter does, but the fact that creatures made of that matter, evolved on a small planet orbiting an ordinary star, have developed the tools and the understanding to perceive forces operating on scales of hundreds of millions of light years. We are embedded in the flow, carried by it, subject to it, but we have also, improbably, understood it. We have mapped what we cannot see. We have measured what we cannot reach. We have given a name to the darkness that pulls us. The Great Attractor remains hidden, but we know it is there. And in that knowledge lies both terror and wonder. The recognition that the universe is vaster, stranger, and more structured than we ever imagined, and that we have somehow managed to glimpse its architecture despite our cosmic insignificance. The journey continues, the fall goes on, and somewhere beyond the veil of stars in a direction we can only infer, the gravity of 100,000 galaxies reaches out across the void, shaping the motion of everything we have ever known. The light from those 100,000 galaxies has been travelling toward us for millions of years, crossing the emptiness between galactic clusters, threading through the cosmic web, only to be stopped at the last moment by the dust and stars of our own home. There is something almost cruel about this arrangement, as if the universe has placed its greatest local mystery just behind the one obstacle we cannot easily move, ourselves. The zone of avoidance, as astronomers call it, is not a region of space. It is a region of our sky, a band where the Milky Way's disk blocks our view of what lies beyond. And the Great Attractor sits almost precisely within that band, at galactic coordinates that place it behind some of the densest star fields and dust clouds in our entire field of view. If you could see invisible light alone, you would never know it was there. But we do not see invisible light alone. The human eye is a remarkable instrument, evolved over millions of years to detect a narrow sliver of the electromagnetic spectrum, the wavelengths that penetrate Earth's atmosphere, that illuminate our daytime world, that reveal the faces of other humans and the movements of predators and prey. Yet that sliver represents only a tiny fraction of the light the universe produces. Beyond the violet end of our vision lies ultraviolet, then X-rays, then gamma rays, energies so high they can ionize atoms, strip electrons from their orbits, reveal the most violent processes in the cosmos. Beyond the red end lies infrared, then microwaves, then radio waves. Wavelengths so long they can pass through dust and gas, as if those obstacles were not there at all. The breakthrough in understanding what lay behind the zone of avoidance came not from building bigger telescopes to see visible light, but from building entirely different kinds of telescopes, instruments sensitive to wavelengths that the dust of the Milky Way cannot block. Infrared light was the first key. Dust absorbs visible light and irradiates it at longer wavelengths, which means the very clouds that hide distant galaxies from our optical telescopes glow brightly in the infrared. But infrared light from those distant galaxies passes through the same dust largely unimpeded. A telescope sensitive to infrared can peer through the murk of the galactic plane and glimpse what lies beyond. In the 1980s, a satellite called IRAS, the Infrared Astronomical Satellite, conducted the first comprehensive survey of the sky at infrared wavelengths. For 10 months in 1983, this joint mission between the United States, the United Kingdom and the Netherlands swept its detectors across the heavens, mapping sources of infrared emission with unprecedented sensitivity. When astronomers analysed the data from the direction of the Great Attractor, they found galaxies, thousands of them, hidden behind the veil, their infrared light penetrating where visible light could not. The zone of avoidance began to yield its secrets. But infrared observations had their limits. The detectors of that era were crude by modern standards, and atmospheric water vapour absorbed many infrared wavelengths before they could reach ground-based telescopes. To see deeper into the zone, astronomers turned to an even longer wavelength, radio. Radio waves pass through dust and gas with ease. They can penetrate not just the Milky Way's disk, but entire galaxies, revealing the distribution of hydrogen gas, the most abundant element in the universe, the raw material from which stars and galaxies form. A galaxy might be invisible in optical light, hidden behind a thick curtain of dust, but if it contains hydrogen, it will emit radio waves at a characteristic wavelength of 21 centimetres. Tune a radio telescope to that frequency, and you can map the presence of matter regardless of what lies in the way. The Parkes Radio Telescope in New South Wales, Australia, became one of the primary instruments for peering behind the zone of avoidance. This massive dish, 64 metres across, had been built in 1961 to support NASA's early space missions, tracking spacecraft and receiving data from the moon. But its true calling proved to be radio astronomy, and in the 1990s it was turned toward the region where the Great Attractor was thought to lie. The surveys it conducted revealed a complex landscape of matter behind the galactic plane, clusters of galaxies, superclusters, voids, and filaments that had been completely invisible to optical instruments. The universe behind the veil was just as rich and structured as the universe we could see directly. What emerged from these observations was not a single massive object, but a vast concentration of galaxies centred on a supercluster called the Norma Cluster, also known by its catalogue designation Abell 3627. This cluster sits roughly 200 million light-years from Earth, almost exactly in the direction that the peculiar velocity measurements had indicated. It contains thousands of galaxies bound together by gravity, surrounded by smaller groups and clusters that together form the overdensity we call the Great Attractor. The mass is not concentrated in one place, but spread across a region tens of millions of light-years in extent, a basin in the landscape of space-time, a valley toward which matter flows. But even as astronomers mapped this structure, they realised something troubling. The Norma cluster and its associated matter could not fully account for the observed flow. The peculiar velocities of galaxies in our part of the universe suggested they were being pulled towards something even more massive than what the surveys had revealed. Either there was more matter hidden deeper within the zone of avoidance, or there was another attractor beyond, something even larger pulling the Great Attractor itself toward a yet more distant destination. The answer, when it came, rewrote our understanding of cosmic structure on the larger scales. The Great Attractor was not the ultimate destination. It was merely a waypoint. In 2014, a team of astronomers led by Brent Tully published a paper that redefined how we think about our place in the universe. Using data from the Cosmic Flows 2 survey, a catalogue of galaxy distances and velocities painstakingly assembled from multiple sources, they mapped the flow patterns of matter across a volume of space 800 million light-years in diameter. What they found was that the Milky Way was not simply falling toward the Great Attractor. It was part of a much larger flow, a river of galaxies converging toward a basin that extended far beyond the Norma cluster. They called this basin Laniakea, borrowing from the Hawaiian language to capture something of its scale. The name means immense heaven, and it was chosen deliberately, an acknowledgement that our cosmic home is part of something vast and structured, that the universe has an architecture we are only beginning to perceive. Laniakea is not a gravitationally bound structure. It will not hold together forever. The galaxies within it are flowing toward a common region, but dark energy will eventually pull them apart, dissolving the supercluster into isolated islands. In this sense, Laniakea is more like a watershed than a kingdom, a region defined by the direction of its flow rather than by permanent boundaries, and at the heart of this watershed, at the lowest point in the gravitational landscape toward which all the matter converges, lies the region we call the Great Attractor. But Tully's team discovered something else, something that made the picture even stranger. The Great Attractor was not the end of the flow. Laniakea itself was being pulled toward an even larger concentration of matter, a structure so massive that it dwarfed everything else in the local universe. This structure had been glimpsed before in surveys that mapped the distribution of galaxies across billions of light-years, but its significance had not been fully appreciated. Tully's team gave it a name that captured its relationship to our cosmic home, the Shapley concentration, named after the astronomer Harlow Shapley, who had first catalogued many of the clusters in that direction a century earlier. The Shapley concentration lies about 600 million light-years from Earth, roughly 3 times farther than the Great Attractor. It is the most massive concentration of galaxies in the observable universe within 1 billion light-years of our position, a supercluster of superclusters containing dozens of rich galaxy clusters bound together by gravity. Its total mass is estimated at more than 10 quadrillion solar masses, a number so large it ceases to have intuitive meaning. To put it in perspective, the Milky Way contains perhaps 200 billion stars. The Shapley concentration contains enough mass to make 50,000 Milky Ways, and all of that mass is pulling on everything in its vicinity, including Laniakea, including the Great Attractor, including our own small galaxy, with its small yellow sun, and its small blue planet where creatures made of carbon and water have somehow figured out what is happening. The flow, it turns out, is a cascade. We are falling toward the Great Attractor, which is falling toward the Shapley concentration, which may itself be falling toward something even more distant that we have not yet mapped. The universe is not static, not uniform, not simple. It is a landscape of hills and valleys, rivers and basins, flows and convergences operating on scales that make human civilization seem like a brief chemical flicker on an insignificant mote, and yet we have measured it. That is the astonishing part. Using radio waves and infrared light, using mathematics and patient observation, using instruments built by hands that evolved to grip branches and throw spears, we have mapped the invisible forces that shape the motion of 1 billion stars. The Great Attractor is hidden, but we know where it is. The Shapley concentration lies beyond, but we have calculated its mass. The cosmic flow carries us toward a destiny we cannot see, but we have traced its direction and measured its speed. Consider for a moment what this achievement represents. 100 years ago, we did not know there were other galaxies. The Great Debate of 1920 saw astronomers arguing whether the spiral nebulae visible in telescopes were merely clouds of gas within the Milky Way or distant island universes in their own right. It was not until Edwin Hubble measured the distance to Andromeda in 1924 that the question was settled. The spiral nebulae were galaxies, millions of light-years away, each containing billions of stars. In less than a century, we went from not knowing galaxies existed to mapping the gravitational flows that link them across hundreds of millions of light-years. The instruments that made this possible are themselves monuments to human ingenuity. The Parkes telescope, which helped reveal the galaxies behind the zone of avoidance, is a dish of steel and aluminum panels 64 metres across, mounted on a rotating turret that allows it to point anywhere in the southern sky. When it was built in 1961, it was the largest steerable radio telescope in the southern hemisphere. Engineers had to solve problems no one had faced before: how to maintain the dish's precise parabolic shape as it tilted and turned, how to shield the sensitive receivers from radio interference, how to process the faint signals arriving from sources millions of light-years distant. The telescope's feed horn, suspended above the dish on a tripod of steel legs, collects radio waves that have been travelling through space for millions of years, focusing them onto receivers cooled to temperatures near absolute zero to minimise electronic noise. The 2-micron all-sky survey, known as 2MASS, mapped the entire sky at near-infrared wavelengths using 2 highly automated telescopes, one in Arizona, one in Chile, that observed every clear night for 4 years. The detectors at the heart of these telescopes were arrays of mercury-cadmium telluride, a semiconductor material sensitive to infrared light, cooled by liquid nitrogen to keep their own thermal emissions from overwhelming the faint signals from distant stars and galaxies. The survey detected over 300 million objects, creating a 3-dimensional map of the local universe that revealed structure behind the zone of avoidance that no optical telescope could see. And then there are the X-ray telescopes, launched into orbit to escape Earth's atmosphere, which blocks high-energy photons. The Rosat satellite, launched in 1990, conducted the first imaging X-ray survey of the entire sky, detecting the hot gas that fills galaxy clusters, gas heated to millions of degrees by gravitational compression, glowing in X-rays that reveal the presence of mass even when individual galaxies are too faint to see. The Chandra X-ray Observatory, launched in 1999, provided images of unprecedented clarity, showing the structure of clusters behind the zone of avoidance in exquisite detail. These instruments orbit above the atmosphere, their mirrors coated with precisely figured layers of heavy metals that reflect X-rays at glancing angles, focusing them onto detectors that can count individual photons. The cumulative effect of all these observations has been to strip away the zone of avoidance's concealment, layer by layer. We cannot see the Great Attractor in visible light, but we can see it in infrared. We can detect its constituent galaxies through their radio emissions. We can map the hot gas in its clusters through their X-ray glow. We can trace its gravitational influence through the motions of everything around it. The veil remains in place, but we have learned to see through it using every tool at our disposal. What have we found? A region of space roughly 150 to 250 million light-years from Earth, centred on a supercluster that contains several major galaxy clusters and countless smaller groups. The Norma cluster is the largest single component, a massive concentration of thousands of galaxies bound together by gravity. Nearby lies the Centaurus cluster, another major structure, along with numerous smaller clusters and groups that together form the overdensity we call the Great Attractor. The total mass is estimated at perhaps 10 quadrillion solar masses, less than the Shapley concentration but still enormous, still significant, still capable of shaping the motions of everything within 100 million light-years. But the more we map, the more we realise how much remains hidden. Even with infrared and radio observations, there are regions of the zone of avoidance so dense with dust and stars that we cannot see through them. There are galaxies we know must exist but have never detected. There are flows and structures that our surveys have not yet resolved. The Great Attractor is no longer a complete mystery, but it is not fully understood either. It occupies an intermediate state, glimpsed but not seen, measured but not comprehended, known but not known. And this brings us to a deeper question, one that lies at the heart of all cosmological inquiry. What does it mean to understand something we cannot directly observe? The Great Attractor will never appear on a photograph, at least not in the way a nearby galaxy might. We will never resolve its individual stars, never see the shapes of its spiral arms or the glow of its nebulae. Our knowledge of it is entirely inferential, built from the motions of other objects, the patterns in surveys, the mathematical models that fit our observations. We know the Great Attractor exists in the same way we know dark matter exists, through its effects rather than its appearance. This mode of understanding is profoundly different from the way we know most things. When you see a chair, photons from that chair enter your eyes, strike your retinas, trigger neural signals that your brain interprets as the experience of seeing. The chair is directly present to your senses, but the Great Attractor is never directly present. What enters our telescopes is light from other galaxies, shifted by their motion, distributed in patterns that imply a gravitational influence. We construct the Great Attractor in our models and equations, and then we say that it exists because no other explanation fits the data. This is not a weakness of our method. It is how science works, especially on cosmic scales. But it does raise questions about the nature of knowledge, about what it means to claim we understand something that lies forever, beyond our direct perception. The philosopher of science, Pierre Duhem, argued in the early 20th century that scientific theories are never tested in isolation. Every observation depends on a web of auxiliary assumptions, about how our instruments work, about the physics governing our measurements, about the relationship between what we observe and what exists. If an observation contradicts a theory, we can always save the theory by modifying one of these auxiliary assumptions. This means that scientific knowledge is always provisional, always embedded in a framework that might itself require revision. The Great Attractor is a perfect illustration of this principle. Our knowledge of its existence depends on assumptions about redshift and distance, about the uniformity of cosmic expansion, about the relationship between light and matter. If any of these assumptions were wrong, our picture of the Great Attractor might change dramatically. We believe we have good reasons for our assumptions. They fit an enormous body of evidence, they make successful predictions, they cohere with the rest of physics. But we cannot prove them beyond doubt. The Great Attractor is, in a sense, a hypothesis. The best explanation for the patterns we observe, but an explanation that could in principle be overturned by new data. This is not cause for skepticism, but for humility. The universe is under no obligation to be simple or fully comprehensible. We probe it with our instruments, we build our models, we refine our understanding, but we always remain embedded in the phenomena we study, limited by the information that reaches us, constrained by the tools we have built. The Great Attractor reminds us of these limits. It is there, exerting its influence, shaping the motion of our galaxy and thousands of others. But it remains partially hidden, partially unknown, a gravitational presence that we detect through its effects without ever seeing its face. And perhaps that is appropriate. Perhaps the universe should contain mysteries that we can glimpse but not fully grasp, forces that we can measure but not observe, structures that we can infer but not photograph. If everything were visible, if every question had a clear answer, the cosmos would be a much smaller and less interesting place. The Great Attractor sits at the edge of our knowledge, beckoning us to look deeper, to build better instruments, to ask better questions. It is not a destination but an invitation, a challenge to the curious creatures who evolved on a small planet and decided to understand the universe that made them. The flow continues, the fall goes on, and somewhere behind the stars, hidden by the very galaxy that gave us life, the gravity of 100,000 galaxies shapes a destiny that we can measure but cannot escape. We are part of the flow, carried by forces we have only recently learned to perceive, falling toward a convergence that will take billions of years to approach and trillions more to resolve. In the meantime, we watch and wonder, building our telescopes and refining our models, reaching out across the electromagnetic spectrum to pierce the veil that hides our fate. The instruments continue their work. In observatories scattered across the Earth and beyond, detectors gather photons that left their sources millions of years ago. Radio dishes track the slow rotation of the sky, mapping the hydrogen that fills the space between galaxies. Infrared sensors cooled to near absolute zero detect the heat of distant stars through the obscuring dust of our own galaxy. X-ray telescopes in orbit collect high-energy photons from gas so hot it glows at temperatures of millions of degrees. Each observation adds another piece to the puzzle, another constraint on our models, another glimpse of the structure that underlies the visible universe. And behind the zone of avoidance, the Great Attractor waits, patient as gravity, silent as space, pulling everything toward a centre we cannot see, but have somehow learned to find. The discovery of the Great Attractor was not a single moment of revelation, but an accumulation of evidence, a slow dawning that took decades to coalesce into something resembling certainty. And even that word, Certainty carries too much weight. What we have is a best approximation, a working model that fits the data we can gather while leaving vast territories of ignorance unmapped. To understand how we came to know what we know, we must return to the middle of the 20th century, when astronomers were just beginning to grasp the true structure of the cosmos. Before they could find the Great Attractor, they had to understand that such a thing could exist at all. They had to build a conceptual framework that would make an invisible, gravitational anomaly a reasonable hypothesis rather than an act of imagination. In the 1950s and 1960s, the prevailing view of the universe was remarkably simple. Galaxies were distributed more or less uniformly throughout space. The cosmos was homogeneous on large scales, lumpy in some places, sparse in others, but averaging out to a smooth and featureless whole when you step back far enough. This was the cosmological principle, the foundational assumption that made general relativity mathematically tractable. Without it, Einstein's equations became impossibly complex, describing a universe with no symmetry, no simplifying structure, no regularity that could be captured in human mathematics. The cosmological principle was a practical necessity, but it was also, in a sense, an act of faith. Astronomers assumed the universe was uniform because the alternative was too complicated to handle, not because they had surveyed enough of it to know for certain. When you can only see a few thousand galaxies and you can only measure distances to a fraction of those, the claim that the cosmos is the same everywhere rests on hope, as much as evidence. But even in those early days, there were hints that something more complex was happening. Galaxies seemed to cluster together in ways that defied random distribution. Some regions of the sky were denser than others. The Virgo cluster, a collection of over 1,000 galaxies about 50 million light-years away, was the most obvious example. A gravitational knot in the fabric of space that pulled smaller galaxies toward it, like leaves circling a drain. Our own local group, the modest collection that includes the Milky Way and Andromeda, was itself falling toward Virgo at several hundred kilometers per second. But Virgo alone could not explain what observers began to notice in the 1970s and 1980s. Something larger was at work, something that affected not just our local group and its immediate neighbours, but vast swathes of the universe, hundreds of millions of light-years across. The first clear indication came from a study of the cosmic microwave background radiation, that faint afterglow of the Big Bang that fills every corner of space with the remnant heat of creation. In 1977, a team of researchers measuring the CMB noticed something unexpected. The radiation was not perfectly uniform. It was slightly hotter in one direction and slightly cooler in the opposite direction. The difference was minuscule, about 3 millikelvins, a few thousandths of a degree, but it was real, and it demanded explanation. The cause, they realized, was motion. The Milky Way was moving through space, and that motion created a Doppler effect in the cosmic microwave background. Just as the siren of an approaching ambulance sounds higher-pitched than a receding one, the CMB appeared slightly compressed, slightly hotter, in the direction we were travelling, and slightly stretched, slightly cooler, in the direction we were leaving behind. This discovery was remarkable for what it revealed about our place in the cosmos. The Milky Way was not at rest. Nothing was at rest. Everything was in motion, falling through space in response to gravitational forces that spanned unimaginable distances. But it was also remarkable for the direction it indicated. The Milky Way's motion relative to the CMB pointed toward a region of the sky in the constellation Centaurus, the same region that would later be identified as the location of the Great Attractor. At first, this motion was attributed to the Virgo cluster. Virgo was massive enough to pull us toward it, and it lay in roughly the right direction. But when astronomers calculated the expected velocity, the speed at which Virgo's gravity should be dragging us, the numbers did not match. We were moving too fast. Virgo's pull accounted for perhaps a third of our motion. Something else, something much larger, was contributing the rest. This was the first crack in the simple picture, the first indication that the universe was not as homogeneous as the cosmological principle suggested. If we were moving faster than Virgo could explain, then Virgo itself must be moving too, pulled by an even more massive structure farther away. The question became, what was pulling Virgo? The answer began to emerge in 1986, when a team of astronomers known as the Seven Samurai published a landmark paper that would reshape our understanding of cosmic structure. The team, Sandra Faber, Donald Lynden Bell, Roger Davies, Alan Dressler, Roberto Turlevich, Gary Wegner, and David Burstein, had spent years measuring the distances and velocities of hundreds of elliptical galaxies scattered across the sky. Their goal was to map the motion of our cosmic neighbourhood, to trace the gravitational currents that carried galaxies through space. What they found was extraordinary. The galaxies were not moving randomly, they were flowing, streaming together in coherent patterns that pointed toward a specific region of space. Not just our local group, not just the Virgo cluster, but a vast collection of galaxies spanning hundreds of millions of light years were all falling in the same direction. The Seven Samurai called this convergent flow a streaming motion, and they gave its apparent destination a name, the Great Attractor. The choice of name was deliberate, even theatrical. Donald Lynden Bell, one of the team's senior members, had a gift for memorable terminology. He wanted a name that captured the mystery and the magnitude of their discovery, something that would stick in the mind and demand attention. The Great Attractor delivered on that promise. It was immediately evocative, suggesting something vast and powerful, something that commanded obedience from galaxies themselves. But the name also carried a subtle warning. By calling it an attractor rather than a cluster or a supercluster, the Seven Samurai were acknowledging that they did not know exactly what they had found. They could measure its effects, they could calculate its approximate location and mass, but they could not observe it directly. The Great Attractor was defined entirely by its gravitational influence, by the way it shaped the motions of everything around it. It was a cause inferred from effects, a centre deduced from the flow of its periphery. The initial calculations were staggering. To explain the observed streaming motion, the Great Attractor would need to contain roughly the mass of tens of thousands of Milky Way galaxies, something on the order of 5 times 10 to the 16th solar masses. That's 50,000 trillion suns concentrated in a region perhaps 150 million light-years across. The number was so large that it strained credibility. How could such a concentration exist without being obvious? How could something so massive hide? The answer lay in the zone of avoidance. The Great Attractor's location, as calculated from the streaming motion, placed it almost directly behind the densest part of the Milky Way's disk, in a region where foreground stars, dust and gas blocked virtually all optical observation. The universe had placed the most massive structure in our cosmic neighbourhood precisely where we could not see it. Whether this was coincidence or some deeper principle at work, the effect was the same. The Great Attractor remained invisible, a presence felt, but not witnessed. The response from the astronomical community was mixed. Some researchers embraced the discovery, recognizing it as evidence for the large-scale structure that newer theories of cosmology had begun to predict. Others were skeptical, questioning whether the streaming motion was real or an artifact of measurement errors. Measuring galactic distances is notoriously difficult, and small errors can compound into large ones when you're trying to detect coherent motion across hundreds of millions of light-years. Perhaps the Great Attractor was a mirage, a statistical ghost that would vanish when better data became available. This skepticism was not unreasonable. The history of astronomy is littered with discoveries that turned out to be errors. The canals of Mars, the planet Vulcan inside Mercury's orbit, countless other claims that seemed solid until they crumbled under scrutiny. The Great Attractor, invisible and inferred, was exactly the kind of discovery that might not survive replication. If subsequent studies failed to confirm the streaming motion, the whole edifice would collapse, but the subsequent studies did confirm it. Through the late 1980s and into the 1990s, multiple teams using different techniques and different galaxy samples independently verified the existence of large-scale streaming motion toward the Centaurus region. The details varied. Different groups found slightly different velocities, slightly different flow patterns, but the overall picture held. Something massive was pulling us, and it lay in the direction the Seven Samurai had identified. What changed over time was our understanding of what the Great Attractor actually was. The initial picture, a single, extraordinarily massive concentration, gradually gave way to something more complex. As astronomers developed new techniques to peer through the zone of avoidance, they began to see structure where before there had been only darkness. Infrared surveys proved crucial. The dust that blocks visible light is far more transparent to infrared radiation, which has longer wavelengths that can pass through interstellar material more easily. Beginning in the 1990s, surveys like 2MASS, the 2-micron all-sky survey, mapped millions of galaxies in near-infrared light, revealing populations of stars and galaxies that optical telescopes could never detect. These surveys showed that the Great Attractor region was not empty, but filled with galaxies, clusters, and the filamentary structures that characterize the cosmic web on smaller scales. Radio observations added another layer of understanding. Hydrogen gas, the most abundant element in the universe, emits radio waves at a characteristic wavelength of 21 centimeters. Unlike visible light, these radio waves pass through the Milky Way's disk with little absorption, allowing astronomers to detect neutral hydrogen in galaxies that would otherwise be invisible. Radio surveys of the zone of avoidance revealed thousands of previously unknown galaxies, including major clusters that contributed significantly to the gravitational pull we had detected. One of the most important discoveries was the Norma cluster, a massive congregation of galaxies near the calculated centre of the Great Attractor. Named for the constellation in which it appears, Norma contains hundreds of galaxies concentrated in a region only a few million light-years across. For a time, astronomers wondered if the Norma cluster was the Great Attractor, the single massive object responsible for the streaming motion. But further study revealed that Norma, while substantial, was not massive enough to account for the observed velocities. It was a major contributor, but not the whole story. The emerging picture was of a distributed mass concentration, a region where matter was denser than average, but not infinitely concentrated in a single point. The Great Attractor was not a single cluster, or even a single supercluster, but a knot in the cosmic web, a region where multiple filaments of galaxies converged and overlapped. The streaming motion we observed was the result of this combined mass, pulling from a broad region rather than a single location. This revision actually made the Great Attractor more plausible, not less. A single object massive enough to explain the streaming motion would have been difficult to hide, even behind the zone of avoidance. But a distributed concentration, spread across hundreds of millions of light-years, could easily escape detection when parts of it were obscured. The Great Attractor's invisibility was not a problem to be solved, but a natural consequence of its structure, and of our unfortunate position behind the Milky Way's disk. The late 1990s and early 2000s brought another complication. As surveys extended deeper into space, astronomers began to detect structures even larger than the Great Attractor. The most significant was the Shapley supercluster, a massive concentration of galaxies about 650 million light-years away, 4 times farther than the Great Attractor itself. Shapley is the most massive collection of galaxies in the observable universe within that distance range. It contains thousands of individual galaxies, dozens of clusters, and an estimated total mass of more than 10,000 trillion suns. When astronomers calculated its gravitational influence on our motion, they found something remarkable. The Shapley supercluster contributed almost as much to our streaming velocity as the Great Attractor did. This discovery did not invalidate the Great Attractor's existence, but it did complicate the picture. We were not falling toward a single destination, but responding to a hierarchy of masses at different distances. The Great Attractor pulled us from 150 million light-years away. The Shapley supercluster pulled us from 650 million light-years. Other structures, more distant and harder to detect, might be pulling as well. Our motion through space was the vector sum of all these influences, each contributing according to its mass and distance. The relationship between the Great Attractor and the Shapley supercluster remains a subject of active research. Some astronomers argue that the Great Attractor should be considered part of a larger structure, the Laniakea supercluster, a term coined in 2014 to describe the basin of attraction that contains our local group, the Virgo cluster, the Great Attractor, and thousands of other galaxies. In this framework, the Great Attractor is not a separate entity, but the gravitational centre of Laniakea, the point toward which everything within the supercluster is falling. But even Laniakea is not the final word. The Shapley supercluster lies outside Laniakea's boundaries, suggesting that our supercluster is itself falling towards something larger. The gravitational hierarchy extends outward without clear limit, each structure embedded in a larger structure, each flow merging into a greater flow. The Great Attractor, once imagined as the ultimate destination, becomes a waypoint on a longer journey, a local centre that is itself in motion toward more distant masses. This nesting of structures challenges our intuition about scale and significance. We speak of the Great Attractor as though it were a single thing, a definite object with a location and mass. But in reality, it is a region, a concentration, a node in a network that extends beyond our ability to map completely. The boundaries we draw around it are somewhat arbitrary, lines on a map that help us talk about cosmic structure, but do not correspond to physical walls or edges. The universe does not come with labels attached. It does not divide itself into neat categories of cluster and supercluster, attractor and background. These are human concepts, tools for organising an overwhelming complexity into patterns we can comprehend. The Great Attractor exists, in the sense that there is a real concentration of mass in the direction of Centaurus that really does influence our motion. But its boundaries blur, its edges fade, its identity merges with the larger structures of which it is a part. This is the nature of scientific knowledge at the frontier. We construct models that capture some features of reality while inevitably simplifying others. The Great Attractor of the 1986 Seven Samurai paper is not quite the same as the Great Attractor of current understanding. The name persists, but the concept has evolved, becoming more complex and more embedded in a larger framework. A generation from now, our picture may change again, refined by new observations and new theoretical insights. What remains constant is the phenomenon itself, the streaming motion, the gravitational pull, the convergent flow of galaxies toward a centre that resists our observation. Whatever we call it, however we draw its boundaries, the mass is there. Its gravity is real. Its effects are measurable. We are falling toward it at this moment, as we have been falling for billions of years. The instruments that reveal this reality continue to improve. Space-based telescopes free from atmospheric distortion map the infrared sky with unprecedented precision. Radio interferometers spanning continents achieve resolutions impossible for single dishes. X-ray observatories detect the hot gas that traces the largest structures in the universe. Each new capability peels back another layer of the zone of avoidance, revealing galaxies and clusters that had been hidden since we first turned our eyes to the sky. The European Space Agency's Gaia mission, launched in 2013, is measuring the positions and motions of over 1 billion stars with precision undreamed of a generation ago. Though Gaia focuses on our own galaxy, its data help calibrate distance measurements throughout the cosmos, reducing the uncertainties that plagued earlier estimates of streaming motion. The more precisely we know where things are, the more accurately we can trace the gravitational influences that shape their paths. Ground-based surveys are mapping the positions of millions of galaxies, building three-dimensional models of cosmic structure that reveal the filaments, walls, and voids that organize matter on the larger scales. These surveys push deeper into the zone of avoidance each year, finding galaxies that have been hidden by the Milky Way's obscuring bulk. With each discovery, the Great Attractor region becomes less mysterious, its structure more clearly defined. Yet mysteries remain. The exact mass distribution within the Great Attractor region is still uncertain. The role of dark matter, invisible matter that makes up most of the mass in the universe, adds another layer of complexity. We know dark matter exists from its gravitational effects, but we cannot see it or detect it directly. The Great Attractor's pull comes primarily from dark matter, not from the visible galaxies that trace its presence. The galaxies are markers, signposts indicating where mass is concentrated, but they represent only a small fraction of the total. Understanding how dark matter is distributed within and around the Great Attractor is one of the major challenges facing cosmology. Computer simulations can model how dark matter should behave, predicting the shapes and sizes of the halos that surround galaxies and clusters. These simulations match observations remarkably well on many scales, but the larger structures, the superclusters and attractors that organize the cosmic web, remain difficult to model precisely. The chaotic nature of gravitational interactions on such scales defeats easy prediction. There is also the question of what will happen as the universe continues to expand. The streaming motion toward the Great Attractor is real, but it is embedded in a larger context of cosmic expansion. Space itself is stretching, carrying galaxies apart from each other at speeds that increase with distance. This expansion works against gravitational attraction, pulling against the bonds that hold structures together. Within gravitationally bound systems, individual galaxies, clusters, even perhaps superclusters, the attractive force overcomes the expansion, keeping matter clumped together. But on the larger scales, expansion wins. The most distant galaxies are receding from us faster than light itself, carried away by the stretching of space faster than any signal could travel. We will never reach them, never interact with them, never receive any information from them after a certain point in the future. The Great Attractor exists in the intermediate regime, where gravity and expansion compete on nearly equal terms. Our galaxy is falling toward it, pulled by its mass. But the universe is also expanding, stretching the space between us. The net effect is that we approach the Great Attractor more slowly than we would in a static universe, and we may never actually arrive. Calculations suggest that the expansion of the universe will eventually dominate even on relatively small scales. Galaxies that are now gravitationally bound may be torn apart in the distant future, their stars scattered into an ever-emptying void. The Great Attractor, along with everything else, will participate in this ultimate dispersal. But that future lies unimaginably far ahead, trillions of years, perhaps longer. On human timescales, on the timescales of civilizations and even of stellar evolution, the Great Attractor remains a fixed presence, a gravitational constant in a universe of change. It will continue to shape the motion of galaxies long after our sun has died and our planet has been consumed by its expanding corpse. It was pulling galaxies toward itself billions of years before Earth formed, and it will continue for billions of years after any trace of humanity has vanished. There is a strange comfort in this persistence. The universe is indifferent to our existence, unconcerned with our hopes and fears, oblivious to the meanings we construct. But it is also stable, governed by laws that do not change capriciously, shaped by forces that operate with mathematical precision. The Great Attractor does not care about us, but it also does not threaten us. Its influence is too slow, too vast, too distributed across time and space to affect anything on human scales. We can study it, map it, name it, theorize about it, and it will continue exactly as it would if we had never existed. This is the relationship we have with the cosmos. We are observers, not participants. We witness processes that unfold on scales utterly beyond our influence. We can understand them to varying degrees, but we cannot change them. The Great Attractor will pull the Milky Way toward it regardless of what we think or do. Our telescopes do not alter its mass. Our theories do not shift its position. Yet there is power in understanding even without control, to know that we are falling, to measure the speed and direction of our fall, to map the mass that pulls us. This is itself an achievement, a triumph of the curious mind over the limitations of position and perception. We are small and brief, but we have reached out across millions of light years to grasp, however imperfectly, the structure of the universe that contains us. The Great Attractor was hidden from us by an accident of position, the alignment of its location with the Milky Way's disk. But we found it anyway, inferring its presence from the motions it induced, deducing its mass from the velocities it created, mapping its approximate location despite the obscuring dust and stars. This is what science does. It finds what is hidden. It names what cannot be seen. It builds models of reality that extend beyond the immediate testimony of the senses. The zone of avoidance is thinner now than it was a generation ago, not because the stars and dust have moved, but because our instruments have improved. What was invisible has become partially visible. What was unknown has become partially known. The Great Attractor emerges from the darkness, not as a clear image, but as a shadow gaining definition, a shape becoming recognizable against a background of greater darkness, and still we look deeper. Still we build better instruments, refine our techniques, extend our reach into the regions that remain hidden. The Great Attractor will yield more of its secrets in the years ahead. The zone of avoidance will grow thinner still. The map will become more detailed, the model more precise. But some mysteries may endure. The universe is vast enough to contain things we will never fully understand. Processes too complex for our mathematics, structures too large for our instruments, timescales too long for our patience. The Great Attractor, even fully mapped, will retain an element of wonder, a reminder that we live in a cosmos capable of producing phenomena beyond our everyday comprehension, forces that shape galaxies as easily as wind shapes clouds. The flow continues. the fall persists. Somewhere beyond the stars we can see, hidden by the galaxy that gave us existence, the gravity of 10,000 galaxies bends space-time into a basin from which nothing escapes. We are part of that flow, carried on currents we have only recently learned to measure, falling toward a future we can calculate but cannot alter. The men and women who first detected the Great Attractor's influence worked with instruments that would seem primitive by today's standards, yet their methods revealed something that generations of astronomers had missed entirely. They measured the velocities of galaxies, painstaking work that required decades of accumulated data, careful corrections for the expansion of the universe itself, meticulous accounting of every source of error. And when they plotted those velocities on their maps, they found the impossible. Galaxies moving in ways that defied the simple picture of cosmic expansion. The universe was not just stretching, it was flowing. The discovery emerged gradually, as most discoveries do. Alan Dressler and the so-called Seven Samurai, the nickname given to the team of astronomers who published their findings in 1988, did not set out to find the Great Attractor. They were studying elliptical galaxies, trying to understand the relationship between a galaxy's luminosity and the speeds at which stars orbit within it. This relationship, called the Faber-Jackson relation after the astronomers who first described it, offered a way to estimate distances to galaxies independent of their redshift. And distance, in cosmology, is everything. If you know how far away a galaxy is, and you know how fast it appears to be receding from us, you can calculate how much of that recession is due to the expansion of space and how much is due to the galaxy's own peculiar motion through space. The distinction matters enormously. When you look at a distant galaxy and measure its redshift, the stretching of its light toward longer, redder wavelengths, you cannot immediately tell why that light is redshifted. Part of the shift comes from the expansion of space itself, the stretching of the universe that carries all galaxies apart from one another. But part might come from the galaxy's own velocity, its movement through space toward us or away from us. To separate these components, you need an independent measure of distance, and that was what the Seven Samurai were working to provide. Their data told an unexpected story. Galaxies in a vast region of space, spanning hundreds of millions of light-years, were all moving in roughly the same direction, relative to the cosmic microwave background radiation, the thermal echo of the Big Bang that serves as a kind of universal reference frame. This streaming motion, as it came to be called, suggested that something massive was pulling on all these galaxies, tugging them off the paths they would otherwise follow as passive participants in cosmic expansion. The Seven Samurai called this hidden mass the Great Attractor, and they placed it roughly in the direction of the Centaurus and Hydra constellations, directly behind the disk of the Milky Way, in the heart of the zone of avoidance. It was a bold claim, and it was controversial from the moment it was published. Other astronomers questioned their distance estimates, their velocity measurements, their interpretation of the data. Some proposed alternative explanations. Perhaps the streaming motion wasn't real, but an artifact of systematic errors in the distance measurements. Perhaps the galaxies weren't being pulled toward a mass concentration, but pushed from behind by a void, a region of space emptier than average, whose relative lack of gravity would have the same effect as an attraction from the opposite direction. The debates that followed consumed years of research effort. Teams of astronomers around the world remeasured the distances and velocities, refined their techniques, gathered more data. And gradually, a consensus emerged. Not complete agreement, but a broad acknowledgement that something massive did indeed lurk in that hidden region of space. The Great Attractor was real, even if its exact nature and extent remained uncertain. What those early discoverers could not know, working with the instruments available in the 1980s and 1990s, was just how much more complex the picture would become. The Great Attractor was not simply a mass sitting in space, pulling galaxies toward it like a drain pulls water. It was itself in motion, falling towards something even larger, embedded in a flow that extended across 500 million light-years of space. The map they had begun to draw would expand in ways they could not have anticipated, revealing structures that dwarfed even their most expansive estimates. But to understand how astronomers came to see this larger picture, we must first understand how they came to see through the zone of avoidance itself, how they developed the tools and techniques that allowed them to peer through the veil of our own galaxy and glimpse the hidden universe beyond. The electromagnetic spectrum is far broader than visible light. Human eyes evolved to detect a narrow band of wavelengths, the portion of the spectrum where the sun emits most of its energy and where Earth's atmosphere happens to be relatively transparent. But the universe radiates across all wavelengths, from radio waves kilometers long to gamma rays with wavelengths smaller than atomic nuclei. And different wavelengths interact differently with the matter that fills space, including the gas and dust of our own galaxy. Visible light is easily scattered and absorbed by interstellar dust. The tiny grains of carbon, silicon and ice that float between the stars are just the right size to interact strongly with wavelengths in the visible range. A photon of blue light encountering a dust grain may be absorbed, its energy converted to heat, or it may be scattered off in a random direction, never reaching the telescope that was waiting to collect it. Red light fares somewhat better. Its longer wavelength makes it slightly less likely to be affected, which is why the Milky Way's dusty disk appears reddish in photographs. But even red light is significantly attenuated as it passes through the thick dust lanes near the galactic plane. Infrared light, with wavelengths longer than red visible light, passes through dust far more easily. A dust grain that would completely absorb a visible photon may allow an infrared photon to slip past almost unaffected. This is why infrared astronomy opened the first windows into the zone of avoidance. In the 1990s, large-scale infrared surveys began to map the sky with unprecedented completeness, revealing galaxies that had been completely invisible to optical telescopes. The 2-micron all-sky survey, known as 2MASS, was one of the most important of these efforts. Using telescopes in Arizona and Chile equipped with infrared detectors, astronomers systematically observed the entire sky at 3 infrared wavelengths. The resulting catalogue contained over 470 million point sources, mostly stars, and more than 1.6 million extended sources, many of which were galaxies. For the first time, astronomers could see large numbers of galaxies behind the Milky Way's disk, their infrared light penetrating dust that would have hidden them completely from visible light observations. The improvement was dramatic, but not complete. Even at infrared wavelengths, the densest parts of the zone of avoidance remained impenetrable. Stars crowded so thickly near the galactic plane that they blended together into an unresolvable glow, hiding any galaxies that might lie behind them, and certain types of dust, particularly the molecular clouds where new stars are forming, remained opaque even to infrared light. The zone of avoidance had shrunk, but it had not disappeared. Radio astronomy offered another approach. Radio waves, with wavelengths measured in centimetres or metres, pass through dust essentially without interaction. A radio telescope can detect emissions from galaxies directly behind the Milky Way's thickest dust lanes, completely unaffected by the obscuring material that blocks visible and even infrared light. But radio observations have their own limitations. The resolution of a telescope, its ability to distinguish fine detail, depends on the ratio of wavelength to aperture. Radio waves are so long that even a radio telescope hundreds of meters in diameter produces images far blurrier than a modest optical telescope. More importantly, not all galaxies are strong radio sources. Most galaxies emit most of their energy at optical and infrared wavelengths, where stars dominate the output. Only galaxies with active nuclei or ongoing star formation produce enough radio emission to be easily detected. The solution increasingly has been to combine observations across multiple wavelengths, building a composite picture that no single type of observation could provide. Infrared surveys find the galaxies. Radio observations measure their velocities through the Doppler shift of the 21-centimetre hydrogen line. X-ray telescopes detect the hot gas that fills clusters of galaxies. Optical spectroscopy, where possible, provides detailed information about stellar populations and chemical compositions. Each wavelength offers a different window into the universe, and together they reveal what any single window would miss. Through these combined efforts, the region around the Great Attractor has slowly come into focus. The Norma cluster emerged from the infrared surveys as a massive concentration of galaxies, a core of gravitational attraction that helps explain the peculiar velocities measured decades earlier. X-ray observations revealed the hot intracluster medium, gas heated to tens of millions of degrees, by the gravitational energy released as it falls into the cluster's potential well. Radio surveys mapped the distribution of neutral hydrogen in and around the cluster's member galaxies. Piece by piece, the picture assembled itself from data gathered across the entire electromagnetic spectrum. Yet even with all these tools, the Great Attractor region remains challenging to study. The Norma cluster lies at a galactic latitude of only about -5 degrees, barely above the galactic plane itself, in one of the most heavily obscured regions of sky accessible from Earth. Many of its member galaxies have never been optically observed. Their existence is inferred from infrared detections, radio emissions, X-ray signatures, all the indirect evidence that modern astronomy can bring to bear on a region that stubbornly refuses to reveal itself directly. The process of studying the Great Attractor has thus become a kind of archaeological excavation, brushing away layers of obscuration to reveal fragments of structure beneath. Each new survey, each improved instrument, each refined technique removes another layer of dust and confusion, exposing more of the underlying reality. But unlike an archaeological dig, where the object of study sits patiently waiting to be uncovered, the Great Attractor extends across such vast distances that even our best observations capture only a fraction of its total extent. We map one corner while another remains hidden. We measure the velocities of galaxies in one region while adjacent regions remain unstudied. The picture we have constructed is necessarily incomplete, a mosaic with missing pieces, a map with unexplored territories still marked as terra incognita. The incompleteness would matter less if the Great Attractor were an isolated phenomenon, a single mass sitting alone in space. But the universe is not so simple. The Great Attractor is embedded in a network of structures that extends across the observable cosmos. Walls and filaments of galaxies, voids and supervoids of relative emptiness, clusters and superclusters arranged in patterns that reveal the initial conditions of the universe itself. The quantum fluctuations of the first moments frozen and amplified across 14 billion years of cosmic evolution. To understand the Great Attractor's role in this larger architecture, astronomers have had to map not just the region immediately behind the Milky Way, but the entire local universe, tracing the flows of matter across hundreds of millions of light years. This is the project that has occupied the past 3 decades of observational cosmology. The construction of ever more detailed maps showing the positions, velocities, and masses of galaxies, clusters, and superclusters in our cosmic neighbourhood. The term neighbourhood requires immediate qualification. In everyday language, a neighbourhood spans blocks, or at most a few miles. In cosmology, the local universe, the region close enough for detailed study, extends across hundreds of millions of light years, containing billions of galaxies. The Milky Way's position in this vast space is not special in any physical sense, but it is privileged in one important way. It is where we are. Everything we know about the universe we know from this vantage point. Every observation we make from here. The cosmic web looks different from different positions, reveals different structures depending on the direction of view. Understanding our particular position within the web is essential to understanding what we see when we look outward. The Milky Way belongs to the local group, a small cluster of galaxies dominated by our own galaxy and the nearby Andromeda galaxy. The local group is itself part of a larger structure called the Virgo supercluster, named for the Virgo cluster of galaxies that dominates its central region. The Virgo supercluster contains at least 100 galaxy groups and clusters, spread across approximately 110 million light-years of space. For decades, this was thought to be our cosmic address, the local group within the Virgo supercluster, a moderately large structure in an otherwise anonymous region of the universe. But the surveys of the 1980s and 1990s revealed that this picture was far too limited. The Virgo supercluster was not an isolated structure, but part of a larger flow, a streaming motion shared by thousands of galaxies across a much more extensive region. And that flow pointed toward the Great Attractor, the hidden mass concentration pulling on everything in its vicinity, including our own local supercluster. The realization transformed astronomers' understanding of cosmic geography. The Virgo supercluster was not a destination but a waypoint, a local concentration of matter embedded in a far larger structure whose full extent was only beginning to emerge. The Great Attractor was not the end of the journey, but another waypoint, itself being pulled towards something even more massive in the direction of the Shapley concentration, a vast assemblage of superclusters roughly 650 million light-years away, containing some of the most massive galaxy clusters known. Mapping these flows required a new approach to cosmological cartography. Traditional galaxy surveys recorded positions and redshifts, building 3-dimensional maps of the cosmic web. But to trace the flows of matter, astronomers needed to measure velocities independent of redshift, the peculiar velocities that reveal motion through space rather than motion with the expansion of space. This meant measuring distances through methods like the Tully-Fisher relation, which relates a spiral galaxy's rotation speed to its intrinsic luminosity, or the fundamental plane relation for elliptical galaxies, which connects their sizes, luminosities, and stellar velocity dispersions. These methods are labour-intensive, requiring detailed observations of individual galaxies rather than the wholesale collection of redshifts that modern surveys can accomplish. But they provide something redshifts cannot: an independent measure of distance that reveals the true velocities of galaxies through space. The most ambitious of these efforts, the Cosmic Flows project led by Brent Tully and his collaborators, has assembled peculiar velocity measurements for tens of thousands of galaxies, creating maps of the cosmic flow field across an enormous volume of space. These maps reveal the gravitational landscape of the local universe, the hills and valleys of space-time that guide the motions of galaxies like water flowing across a tilted surface. What the Cosmic Flows maps show is a universe in constant motion, with galaxies streaming along invisible channels carved by the distribution of mass. The Great Attractor appears in these maps as a basin of attraction, a region toward which matter flows from a wide catchment area. But it is not the only such basin. The Shapley concentration creates an even deeper well, pulling on the Great Attractor itself and on everything falling toward it. The entire local universe is engaged in a vast gravitational dance, with structures falling toward larger structures, which are themselves falling toward still larger structures, in a hierarchy that extends to the largest scales astronomers have yet mapped. The Cosmic Flows project produced one of the most striking visualizations in modern cosmology, a definition of the Laniakea supercluster, the structure to which our galaxy belongs. Named from Hawaiian words meaning immense heaven, Laniakea encompasses the Virgo supercluster, the Great Attractor region, and numerous other clusters and filaments, all united by their shared participation in the flow toward the Great Attractor's basin. The boundary of Laniakea is not a physical wall but a watershed divide, the line separating regions that flow toward the Great Attractor from regions that flow toward other basins of attraction. Just as rivers flow downhill toward different oceans depending on which side of a continental divide they begin, galaxies flow toward different attractors depending on their position in the cosmic flow field. Laniakea spans approximately 520 million light-years and contains roughly 100,000 galaxies with a total mass of about 100 million billion solar masses. It is one of the largest coherent structures ever identified in the universe, not in the sense of being gravitationally bound, for it is far too large to ever collapse into a single object, but in the sense of being dynamically connected, its parts linked by their shared participation in the same gravitational flow. The definition of Laniakea changed our understanding of cosmic geography in a fundamental way. Previously, superclusters were defined by the positions of galaxies, concentrations of matter identified visually or through density analysis of galaxy surveys. But the Cosmic Flows approach defined superclusters by their dynamics, by the flows of matter that reveal the underlying gravitational landscape. This is a more physically meaningful definition, one that captures the causal connections between structures rather than merely their spatial proximity. Standing at the centre of Laniakea, or rather falling through its interior alongside every other member of the local group, we can now see our cosmic context with unprecedented clarity. The Great Attractor is not simply a mass pulling on us from across the void. It is the gravitational centre of our supercluster, the basin toward which we are falling, the focus of the flow that defines our membership in Laniakea. We belong to it not by accident of position, but by physical connection, our velocity vector shaped by the mass distribution that creates its attraction. Yet this belonging is not permanent. The expansion of the universe works against the Great Attractor's pull, stretching the space between us and our destination even as gravity accelerates us toward it. In the very long term, on timescales of hundreds of billions of years, dark energy will win this contest. The universe's accelerating expansion will eventually overwhelm all local flows, carrying the Great Attractor away from us faster than gravity can pull us toward it. The flow that defines Laniakea will cease, the basin will become inaccessible, our supercluster will dissolve into the general expansion. But that dissolution lies in the unimaginably distant future. For now, and for billions of years to come, The flow continues. We fall toward the Great Attractor at hundreds of kilometers per second, part of a river of galaxies pouring into a basin we can barely see. The maps grow more detailed with each passing decade. The flow field reveals more of its structure with each new survey, and slowly, through the accumulated effort of thousands of astronomers working across generations, the hidden architecture of our cosmic home emerges from the darkness that once concealed it. The process of discovery continues even now, as new instruments come online and new techniques are developed. The Dark Energy Spectroscopic Instrument, operational since 2021, is gathering spectra for tens of millions of galaxies, building the most detailed map of the cosmic web ever constructed. The Vera Rubin Observatory, beginning operations in the mid-2020s, will image the entire visible sky repeatedly over a decade, detecting billions of galaxies and enabling new measurements of the cosmic flow field. Each new data set adds resolution to the picture, fills in blanks on the map, extends the reach of our understanding into previously unexplored regions. The zone of avoidance remains a challenge, but it is a shrinking one. Infrared surveys push deeper into the obscured regions. Radio telescopes resolve individual galaxies, where optical observations see only confusion. Indirect methods, including the reconstruction of mass distributions from their gravitational effects on the cosmic microwave background, provide information about regions no telescope can directly observe. The Great Attractor, once completely hidden, now appears in our maps as a partially revealed structure, its shape emerging from the shadows like a figure approaching through fog. What we find there may yet surprise us. The history of Great Attractor research is a history of revised estimates and expanded horizons. Masses that proved smaller than first thought, structures that proved larger, connections that reached farther than anyone anticipated. The Great Attractor of the Seven Samurai's original paper was a single massive object, a kind of cosmic magnet pulling everything toward it. The Great Attractor we understand today is a node in a network, a waypoint in a flow, a local concentration embedded in a larger structure that extends across hundreds of millions of light years. What future observations will reveal, what structures remain hidden behind the last opaque barriers of the zone of avoidance, what masses lurk in regions our current instruments cannot probe, remains to be seen. The universe guards its secrets carefully, revealing them only to those patient enough to look with the right instruments, creative enough to find indirect paths around obstacles, persistent enough to return again and again to the same questions with improved tools and refined techniques. The Great Attractor was found this way, through decades of accumulated effort, through setbacks and controversies, and slow convergence toward consensus. And it will be understood this way too, through the same patient accumulation of evidence, the same gradual refinement of models, the same interplay of theory and observation that has characterized all our greatest scientific achievements. The fall continues. The galaxies stream, somewhere in the dark, hidden by the very stars that give us light. The mass that shapes our motion waits to be fully seen. The act of falling is so fundamental to the universe that we rarely pause to consider its strangeness. A stone dropped from a height accelerates toward the Earth, not because anything pushes it, but because the presence of mass has curved the very geometry of space, and the stone is simply following the straightest possible path through that curved geometry. Einstein showed us this a century ago, replacing Newton's mysterious action at a distance with something even more profound. The universe is a dynamic fabric, shaped and reshaped by the matter and energy within it. Every galaxy, every star, every atom of hydrogen drifting in the intergalactic medium follows these geometric paths, tracing the contours of a landscape carved by mass. We are tracing such a path now, our entire galaxy a mote of dust sliding down an invisible slope toward a destination we cannot fully perceive. The Milky Way does not know it is falling. The 300 billion stars that constitute our galactic home feel no acceleration, no wind of passage, no sense of motion whatsoever. This is the profound peculiarity of gravitational fall. Everything falls together. Your body falls toward the Great Attractor at 600 kilometers per second, but so does the chair beneath you, the floor beneath that, the bedrock beneath the floor, the mantle and core of the Earth, the sun around which we orbit, and every other object in the local group. Falling together, we experience nothing. Only by looking outward, measuring our motion against the cosmic reference frame established by the ancient light of the cosmic microwave background, do we discover that we move at all? This shared, imperceptible motion connects us to something vast. The same gravitational field that curves our trajectory has curved the paths of hundreds of thousands of other galaxies, drawing them into a coherent flow across hundreds of millions of light years. When astronomers map this flow, they find patterns of startling elegance, streamlines converging toward basins, diverging from voids, tracing the three-dimensional architecture of the cosmic web with a fidelity that no galaxy survey alone could achieve. The flow field and the density field are two representations of the same underlying reality, two languages describing the same cosmic structure. Learn to read one, and you can infer the other. This is why peculiar velocity surveys have become such powerful tools for cosmography. They reveal mass wherever it hides, including in regions where no light escapes to betray its presence. But reading the flow field requires measuring velocities, and measuring velocities requires observing galaxies. This brings us back, always, to the fundamental challenge that has shaped Great Attractor research from its inception. The zone of avoidance. That band of obscurity 20 degrees wide and circling the entire sky contains precisely the regions we most need to study. The Great Attractor lies behind it. The full extent of the Shapley concentration lies partially within it. The connecting structures that would reveal the complete architecture of our cosmic environment remain hidden in its depths. Astronomers have attacked this problem from every possible angle, quite literally. Infrared observations at wavelengths of 1, 2, and 25 microns progressively penetrate the dust, revealing galaxies that optical surveys miss entirely. The 2-micron all-sky survey, completed in 2003, detected over 1 million extended sources across the zone of avoidance, resolving individual galaxies in regions previously known only as featureless glows. Its successor surveys have pushed deeper still, finding objects where extinctions exceed 10 magnitudes at visible wavelengths, galaxies so thoroughly buried in foreground dust that they contribute nothing to the visible sky, but reveal themselves clearly in infrared light. Radio observations offer another path through the murk. The 21-centimetre hydrogen line, that signature frequency emitted by neutral hydrogen atoms throughout the cosmos, passes through dust as though it weren't there. A galaxy rich in hydrogen gas betrays itself through radio emission, regardless of how much interstellar material blocks our optical view. The Parkes Observatory in Australia and the Arecibo Observatory in Puerto Rico, before its tragic collapse in 2020, mapped thousands of previously unknown galaxies within the zone of avoidance through their hydrogen signatures. The Effelsberg Radio Telescope in Germany and the Green Bank Telescope in West Virginia continue this work, finding galaxies hidden behind the thickest parts of the Milky Way's disk, slowly filling in the blanks on our cosmic maps. What these observations reveal is both reassuring and humbling. Reassuring because the zone of avoidance, while certainly hiding significant structures, does not appear to conceal anything so massive that it would revolutionize our understanding of cosmic flows. The Great Attractor and the Shapley concentration, now partially mapped through infrared and radio techniques, remain the dominant features shaping our motion. No hidden supercluster of comparable mass has emerged from the surveys. The basic picture assembled over the past 4 decades appears correct in its broad outlines. Humbling because those broad outlines barely scratch the surface of what we don't know. The surveys that penetrate the zone of avoidance are shallow compared to those that cover the rest of the sky. They detect only the nearest and brightest objects, missing fainter galaxies that would reveal the full extent of the structures they trace. The galaxy clusters hidden behind the thickest regions of dust remain largely uncharacterized. Their masses estimated roughly, their memberships uncertain, their connections to surrounding structures poorly understood. Every new survey that probes deeper into the zone discovers objects that previous surveys missed. The map remains incomplete, its blankest regions precisely those that matter most for understanding our cosmic environment. Consider what it means to live in a galaxy whose disk obscures our view of our own motion through the universe. The stars that make up the Milky Way, the same stars whose nuclear fires make life possible on Earth, whose heavy elements compose our bodies, whose gravitational interactions shaped our solar system's history, are the very objects that prevent us from seeing where we're going. We navigate the cosmos with a windshield made opaque by the source of our own existence. There is something almost mythological in this situation, a scientific parallel to the oracle's warning that complete self-knowledge remains forever out of reach. Yet we persist in looking. The European Space Agency's Gaia spacecraft, launched in 2013 and still operating as of its extended mission phases, has transformed our understanding of our galaxy's structure by measuring the positions and motions of nearly 2 billion stars with unprecedented precision. These measurements, initially focused on understanding the Milky Way itself, also contribute to Great Attractor research in unexpected ways. By precisely mapping the distribution of obscuring dust, Gaia helps astronomers correct their observations of background galaxies, extracting fainter signals from noisier data. By revealing the Milky Way's structure in 3 dimensions, the spacecraft illuminates the geometry of the zone of avoidance, showing where the obscuration is thickest and where windows of relatively clear sightlines might allow deeper views. The interplay between these different approaches, infrared surveys, radio observations, dust mapping, indirect dynamical inference, exemplifies the collaborative nature of modern astronomy. No single technique suffices to characterize the Great Attractor region. Each provides complementary information. Radio observations reveal gas-rich spirals while missing gas-poor ellipticals. Infrared surveys detect the smooth stellar light of ellipticals while struggling to resolve the clumpy emission of star-forming spirals. Dynamical methods infer total mass, including dark matter, while remaining agnostic about how that mass is distributed among galaxies. Only by combining these approaches can astronomers construct a coherent picture of what lies hidden behind our galactic disk. The picture that emerges is one of ongoing discovery, but also of converging understanding. The Great Attractor is not a single object but a region, a concentration of mass centered roughly on the Norma cluster, embedded in a wall of galaxies that extends across a substantial fraction of the nearby universe. Its gravitational influence draws us toward it, but that influence is now understood to be only part of the story. We fall toward the Great Attractor, yes, but both we and the Great Attractor fall together toward the Shapley concentration, that larger collection of clusters whose gravitational reach extends even farther. And beyond Shapley, hints of still larger structures appear in the deeper surveys, suggesting that the flow field we've mapped is itself embedded in flows at even larger scales. This hierarchical arrangement repeats a pattern found throughout the cosmos. Stars orbit in galaxies, galaxies clump in groups and clusters, clusters aggregate in superclusters, superclusters connect through filaments and walls that trace the cosmic web. At each scale, smaller structures move coherently under the gravitational influence of larger ones, their motions revealing the hidden mass that shapes their paths. The Great Attractor sits comfortably within this hierarchy, neither the largest structure in the universe nor the most powerful gravitational influence, but a significant node in the network of matter that pervades all of space. Understanding our place within this network has required confronting some of the deepest questions in cosmology. How much matter does the universe contain? How is that matter distributed? What forces shape its arrangement over cosmic time? These questions, pursued by astronomers studying the cosmic microwave background, the distribution of galaxies, the expansion history of the universe, and the peculiar velocities of nearby objects, have converged toward a consistent picture known as the Standard Cosmological Model. In this picture, ordinary matter, the atoms that compose stars and planets and human beings, constitutes only about 5% of the universe's total content. Dark matter, invisible but gravitationally influential, comprises roughly 27%. The remaining 68% consists of dark energy, that mysterious component driving the universe's accelerating expansion. The Great Attractor, like all the structures we observe, is built primarily from dark matter. The galaxies we see in our surveys trace this dark matter, like illuminated ships revealing the shape of an otherwise invisible ocean. For every gram of luminous matter in the clusters behind the Milky Way's disk, several grams of dark matter accompany it, adding their gravitational influence to the total mass that pulls on us from the Centaurus direction. When we speak of the Great Attractor's mass, we speak of this total, luminous and dark together, because gravity responds to all forms of matter regardless of whether they emit light. This dark matter dominance creates an epistemological challenge of its own. We can observe galaxies directly, counting them, measuring their redshifts, determining their individual masses from rotation curves and stellar velocity dispersions. But the dark matter halos in which they reside reveal themselves only through gravitational effects, the lensing of background light, the dynamics of satellite objects, the peculiar velocities that carry us toward mass concentrations. The Great Attractor's dark matter component remains fundamentally invisible, known only through the paths it carves in the cosmic flow field. We infer its presence from our motion, much as we might infer the presence of a massive object beneath the surface of a flowing river from the disturbance it creates in the water above. The philosophical implications of this situation merit contemplation. We exist within a universe whose dominant components remain essentially invisible to us. Dark matter pervades all space, shaping the formation of galaxies and the evolution of cosmic structure, yet we cannot see it or detect it directly with any instrument currently devised. Dark energy drives the expansion of the universe, determining its ultimate fate, yet its nature remains among the deepest mysteries in physics. The Great Attractor, that massive concentration toward which we fall, consists primarily of substances we cannot observe except through their gravitational signatures. We are residents of a haunted cosmos, surrounded by invisible influences that guide our motion through the dark. And yet, we have learned so much. Through the patient accumulation of evidence, the development of new observational techniques, the construction of ever more powerful instruments, we have mapped our cosmic environment in remarkable detail. We know that we live in a galaxy called the Milky Way, one of dozens in a gravitationally bound assembly called the local group. We know that the local group participates in a coherent flow toward a mass concentration hidden behind our galactic disk, and that this flow is itself part of a larger streaming motion toward an even more massive collection of clusters known as the Shapley concentration. We have identified the boundaries of our cosmic watershed, mapped the velocity field that defines Laniakea, traced the filaments and voids that constitute the cosmic web within hundreds of millions of light years. From our tiny planet orbiting a modest star in the outskirts of an ordinary spiral galaxy, we have perceived the architecture of the cosmos. The contrast between the grandeur of these discoveries and the limitations they reveal defines the contemporary state of Great Attractor research. We understand the basic physics that governs cosmic flows, general relativity, the growth of structure in an expanding universe, the interplay between dark matter and ordinary matter informing the cosmic web. We have mapped the broad outlines of our cosmic environment, identifying the major structures that shape our motion, but the details, the precise mass of the Great Attractor region, the exact shape of the zone of avoidance structures, the full extent of the flows that connect Laniakea to neighbouring superclusters, remain works in progress. Each new survey adds resolution to the picture without bringing it to completion. The final image, if such a thing can ever exist, lies somewhere in the future, awaiting instruments and techniques not yet invented. This incompleteness is not a failure of astronomy, but a fundamental characteristic of scientific knowledge. Every discovery opens new questions. Every answered mystery reveals unexplored territory beyond. The Seven Samurai, publishing their 1988 paper on large-scale streaming motions, could not have anticipated the discovery of Laniakea. The astronomers of the 2030s, working with data from the Vera Rubin Observatory and the Euclid Space Telescope, will surely find structures and patterns that current observations cannot detect. The Great Attractor, once a single puzzling anomaly in our velocity, has become a window onto the architecture of the cosmic web. What new windows will open as technology advances and observations accumulate remains to be seen. For now, we fall. The motion never pauses, never hesitates, never varies. At 600 kilometers per second relative to the cosmic microwave background, the Milky Way slides down the gravitational potential toward a region it cannot directly observe. The journey will never reach its destination. Dark energy will separate us from the attractor before we arrive, but the journey itself reveals the universe's structure. By measuring our fall, we discover what we're falling toward. By mapping our motion, we map the invisible landscape through which we move. This method of discovery, inferring hidden realities from observable motions, has a long history in astronomy. The planet Neptune was found this way. Its existence predicted from gravitational perturbations in the orbit of Uranus before any telescope detected its light. The first exoplanets were discovered this way, their masses inferred from the tiny wobbles they induced in their parent stars. dark matter itself was first proposed to explain the unexpectedly rapid rotation of galaxies, a dynamical anomaly that pointed toward unseen mass. The Great Attractor joins this tradition, a structure revealed not by direct observation, but by the gravitational shadow it casts on everything around it. There is something deeply satisfying about this way of knowing. The universe, vast and largely inaccessible to direct investigation, nonetheless reveals itself to patient observers who learn to read the signs it leaves. A galaxy's velocity, measured through the Doppler shift of its spectral lines, carries information about the total mass distribution along the line of sight. A pattern of velocities across many galaxies maps the gravitational landscape of a region far larger than any individual observation could cover. The same principles that allow us to weigh distant planets from the orbits of their moons allow us to weigh superclusters from the motions of their constituent galaxies. Gravity is the universal messenger, carrying information about mass regardless of whether that mass shines. The Great Attractor exemplifies this principle in its purest form. Hidden behind the zone of avoidance, it would remain completely unknown if gravity operated only on visible matter within visible regions. But gravity reaches through barriers. The mass behind the Milky Way's disk pulls on every galaxy in our neighbourhood, imparting velocities that we can measure from our position on the visible side of the obscuring zone. These velocities, pointing systematically toward a common direction, reveal what direct observation cannot see. The attractor exists because we feel its pull, because our motion demands an explanation, because the universe's laws work consistently throughout space, regardless of what obstacles lie between observer and observed. This gravitational transparency offers reassurance amid the vast darkness of cosmic uncertainty. Even in the regions we cannot see, even in the territories hidden by dust and distance, the same physics operates. Mass curves space. Curved space directs motion. Motion can be measured, and from those measurements structure can be inferred. The Great Attractor is no longer a complete mystery, but a partially characterized feature of our cosmic environment. Its mass roughly estimated, its position approximately known, its relationship to surrounding structures increasingly well understood. The zone of avoidance remains a challenge, but it is a surmountable one. Patient observation, across decades and wavelengths and techniques, has brought the hidden attractor progressively into view. What remains hidden, what lies beyond our current instrument's reach, will yield to future efforts. This is the faith that sustains scientific inquiry, that the universe is comprehensible, that its secrets can be unlocked through careful observation and rigorous reasoning, that the darkness that conceals is not absolute but merely challenges us to develop new ways of seeing. The Great Attractor was once a complete mystery. Now it is a known unknown, a specific gap in our cosmic map rather than an undiscovered territory. The difference matters. A known unknown can be investigated, its boundaries can be defined, strategies for exploring it can be devised. The mystery of our cosmic motion has become a research program, pursued by hundreds of astronomers using instruments that grow more powerful with each passing year. The fall continues, as it has for billions of years, as it will for billions more. Somewhere in the direction of the Southern Cross, hidden by the very stars that ancient mariners used to navigate Earth's oceans, an enormous concentration of matter waits for us. We will never reach it. The universe is expanding too fast, and will soon expand faster still, but we are falling toward it nonetheless. And in that falling, in that persistent motion toward a destination we cannot attain, we have learned truths about the cosmos that observation alone could never reveal. The galaxies stream, the flow continues. The universe, for all its vastness and darkness and hidden depths, reveals itself to those patient enough to watch and measure and think. The Great Attractor, that gravitational anomaly discovered through its influence on our motion, stands as testament to what such patience can achieve. And the work goes on as it must, as it always has, because the questions do not end and the darkness does not concede without a fight. Instrument by instrument, survey by survey, measurement by measurement, we map the hidden architecture of our cosmic home. The mapping reveals patterns within patterns, structures nested like Russian dolls across scales that strain comprehension. And as we trace these patterns outward, following the gravitational threads that bind galaxy to cluster to supercluster, we encounter a truth that transcends the Great Attractor itself. Our cosmic neighbourhood is merely one province in a far larger kingdom, and that kingdom is itself part of an empire whose borders we are only now beginning to glimpse. The name they have given to this empire is Laniakea, a Hawaiian word meaning immeasurable heaven. It was chosen by Brent Tully and his collaborators in 2014 when their analysis of galaxy motions revealed that the Great Attractor was not the final destination of our cosmic fall, but merely a way station, a local concentration of mass embedded within a vastly larger structure. Laniakea encompasses the Great Attractor and extends far beyond it, incorporating superclusters that astronomers once thought were separate entities: the Parvo-Indus supercluster, the Hydra Centaurus supercluster, the Southern supercluster complex. All of these, it turns out, are parts of a single gravitationally bound system, a cosmic continent whose shores are defined not by visible boundaries, but by the watersheds of velocity flow. Picture a terrestrial analogy. Raindrops falling on a mountain range flow downhill, eventually reaching rivers that carry them to the sea, but the exact path they take depends on which side of the ridge they fall. A drop landing inches to the left of a continental divide ends up in one ocean, inches to the right in another. The ridge itself marks a boundary between drainage basins, a line of gravitational indifference where water could flow either way. Laniakea is defined by exactly such boundaries, not ridges of rock but surfaces in space where gravitational influence is balanced, where a galaxy's allegiance to one attractor or another hangs in perfect equilibrium. Within those boundaries, everything flows toward common centres. Beyond them, the flows diverge, carrying matter toward different gravitational basins entirely. The Great Attractor sits within Laniakea's interior, drawing in the matter around it. But the flow does not stop there. Beyond the Great Attractor lies another concentration of mass, larger still, toward which the attractor itself is falling. This is the Shapley concentration, named for Harlow Shapley, the astronomer who first recognised it in the 1930s as an unusual clustering of galaxies in the direction of Centaurus. The Shapley concentration contains dozens of rich galaxy clusters, packed into a region spanning roughly 60 million light-years, representing one of the densest known collections of matter in the observable universe. Its total mass exceeds that of the Great Attractor by a factor of several times, and its gravitational reach extends across hundreds of millions of light-years, adding its pull to the flow that carries us through space. So we fall toward the Great Attractor, and the Great Attractor falls toward Shapley, and the whole vast procession moves through the cosmic deep like a river of galaxies seeking an ocean that may not exist. The hierarchy of attraction extends upward, scale after scale, until we reach distances where the expansion of the universe finally dominates over gravitational collapse, where the cosmic web begins to thin, and the flow disperses into the general Hubble expansion. Somewhere between here and there lies the edge of Laniakea, the boundary of our gravitational basin, the line beyond which galaxies are falling toward other attractors, other concentrations, other destinies. This cascading picture, attractor within attractor, flow within flow, transforms our understanding of what the Great Attractor means. It is not the ultimate centre of our cosmic motion, not the final destination of our gravitational journey. It is instead a feature of intermediate scale, a local maximum of density that dominates our immediate neighbourhood while remaining subordinate to larger structures beyond. The Milky Way falls toward the Great Attractor. The Great Attractor falls toward Shapley. Shapley and the rest of Laniakea fall toward what? The observations are not yet precise enough to say with certainty. The flows become harder to trace at greater distances, the velocities smaller relative to measurement uncertainties, the structures more difficult to disentangle from the general expansion of space. But the principle seems clear. There is no final attractor, no ultimate destination, only an infinite regression of structures and motions extending outward to the edges of observability, and presumably beyond. This realization carries philosophical weight that extends beyond astrophysics. For centuries, humans believed that Earth occupied a central, privileged position in creation, the center of the universe, the focus of divine attention, the stage upon which the cosmic drama unfolded. Copernicus displaced us from that center, revealing Earth as merely one planet among several orbiting an ordinary star. Later discoveries extended the displacement. Our Sun proved to be one among billions in the Milky Way, our galaxy one among trillions in the observable universe. Each step removed us further from cosmic specialness, further from the comforting notion that the universe was built around us. The Great Attractor represents another such step, perhaps the most profound of all. We are not merely orbiting within larger structures, we are falling through them, carried along by forces we did not choose and cannot control. Our trajectory through space is not self-determined, but externally imposed, sculpted by mass distributions established billions of years before our planet formed. We are passengers on a journey whose course was set in the earliest moments of cosmic time, when the primordial fluctuations that would become galaxies and clusters and superclusters were imprinted on the fabric of space itself. The Great Attractor pulls us because it was born from those fluctuations, because the matter that would become us and the matter that would become it shared a common origin in the quantum uncertainties of the infant universe. There is horror in this, yes, the horror of being subject to forces beyond comprehension, of falling toward a destination we cannot see and will never reach. But there is also a strange beauty, a grandeur that elevates rather than diminishes. We are participants in a cosmic dance choreographed by gravity across billions of years, connected by invisible threads to structures spanning hundreds of millions of light years. Our atoms fell toward the Great Attractor long before they were atoms, back when they were merely density fluctuations in a plasma sea. They will continue falling long after those atoms have been dispersed by stellar death and reconstituted into forms we cannot imagine. The falling is our heritage, our connection to the universe's deepest history, our proof that we are woven into the cosmic fabric rather than painted upon it. Consider what it means that we can know these things. A species that arose on a small planet orbiting a medium-sized star in the outer reaches of an ordinary galaxy has managed to detect and characterize a gravitational anomaly hidden behind its own galactic disk, hundreds of millions of light-years distant, invisible to direct observation. This achievement required centuries of accumulated knowledge, the efforts of thousands of scientists across dozens of nations, instruments of exquisite sensitivity deployed on mountaintops and in orbit, computers capable of processing observations from billions of individual objects. It required faith that the universe is comprehensible, that the same laws operate everywhere, that patient inquiry can penetrate even the most formidable barriers, and that faith has been rewarded, not with complete understanding, never that, but with progress, with insight, with the transformation of absolute mystery into characterized phenomenon. The zone of avoidance remains, but we have learned to see through it. The Great Attractor remains hidden, but we have learned to feel its pull. The universe remains vastly larger than we can fully comprehend, but we have learned to map its structures across scales that dwarf our solar system by factors of billions. Each discovery reveals new mysteries, each answer generates new questions, but this is not failure. It is the nature of successful inquiry, the mark of a research program that generates more than it consumes. The Great Attractor was discovered because earlier astronomers had measured cosmic expansion, which required earlier astronomers to identify galaxies as separate systems, which required earlier astronomers to understand that stars are other suns, which required earlier thinkers to realize that Earth is not the center of creation. The chain of understanding extends back across centuries and will extend forward across more centuries to come. We are links in that chain, not endpoints. The fall continues. At this very moment, as you contemplate these words, the Milky Way is hurtling toward the constellation Centaurus at more than 600 kilometers per second, carrying the Sun and Earth and everything humanity has ever known along with it. This motion adds to our other motions, our orbit around the galactic center, our solar system's motion through the local stellar neighborhood, Earth's orbit around the Sun, the rotation that brings day and night. We are moving in multiple ways simultaneously, our trajectories compounded into a single complex path through space-time that would be nearly impossible to describe in full detail. But the component that points toward the Great Attractor is now understood, at least in broad outline. We know why we are falling. We know, approximately, toward what. We know that this fall is one of countless similar falls occurring throughout the universe, that every galaxy everywhere feels the pull of mass concentrations in its vicinity, that the cosmic web is not static but flowing, streaming, converging toward density peaks, and draining away from cosmic voids. The voids are the Great Attractor's opposite number, regions of space where matter is conspicuously absent, where the density falls well below the cosmic average, where galaxies are few and far between. They too contribute to our motion, though by repulsion rather than attraction. A void behind us pushes as effectively as a concentration ahead of us pulls. Both produce the same net effect, acceleration toward the denser region. The dipole repeller, identified in 2017 by Yehuda Hoffman and his collaborators, represents exactly such a region, a vast underdense zone in the direction opposite the Great Attractor, contributing to our motion by its emptiness. We are being pushed from behind as well as pulled from ahead, squeezed between fullness and emptiness, channeled along a gravitational corridor that stretches across half the observable universe. This push-pull dynamic adds nuance to our understanding but does not change its essential character. We are subject to forces operating across cosmic scales, forces that predate our existence by billions of years and will persist for billions more, forces that determine our trajectory regardless of our awareness or consent. The Great Attractor is the most dramatic manifestation of these forces in our local environment, but it is not unique, not special, not singular. It is merely the largest nearby concentration of mass, the dominant feature of our gravitational landscape. In other regions of the universe, other attractors play the same role for other galaxies. The cosmos is full of convergence points, full of streaming flows, full of matter falling toward matter in patterns established in the first fraction of a second after the Big Bang. Those patterns carry information about the earliest moments of cosmic time, information that has been preserved across nearly 14 billion years of expansion and evolution. The density fluctuations that seeded the Great Attractor were imprinted on the universe when it was far less than a second old, when the physics of the very small governed the behavior of the very large, when quantum uncertainty left permanent marks on the fabric of space. By studying structures like the Great Attractor today, by mapping their positions and measuring their masses and tracing the flows they generate, we peer backward through time to those primordial moments. The Great Attractor is a fossil, a relic, a message from the dawn of creation written in the language of gravity and motion. Reading that message tells us not only about our cosmic neighbourhood, but about the fundamental nature of the universe itself, its geometry, its composition, its history, its ultimate fate. And what does that message say about our fate? Here the horror deepens, though perhaps horror is not the right word. Perhaps melancholy is more apt, or resignation, or simply acceptance. The universe is expanding, and that expansion is accelerating. Dark energy, whatever it is, and we do not know what it is, only that it exists and acts, drives space itself to stretch at an ever-increasing rate. In the distant future, this expansion will overwhelm gravity. The flows that currently carry us toward the Great Attractor will slow, then stop, then reverse. Galaxies that are now falling together will begin to recede from one another, carried apart by the inexorable swelling of space. The Great Attractor will lose its grip on us, its gravitational reach exceeded by the expansion of the void between us. We will drift apart, our cosmic neighbourhood dissolving into isolation. This is not imminent. Billions of years will pass before the expansion decisively wins, before the local group of galaxies, the Milky Way, Andromeda, and our smaller companions, is all that remains bound together in an ever-emptying cosmos. In the near term, cosmically speaking, we will continue to fall toward the Great Attractor, and the Great Attractor will continue to fall toward the Shapley concentration, and the great streaming flows of the cosmic web will persist. But the universe is patient, and dark energy is relentless. Eventually the flows will cease. Eventually each galaxy will be alone with its companions, surrounded by an expanding void of absolute emptiness. Eventually the cosmic web itself will dissolve, its filaments stretched beyond recognition, its nodes scattered like seeds on an infinite wind. The Great Attractor, that tremendous concentration of mass that has shaped our cosmic motion for billions of years, will become irrelevant. Its gravity will reach out across space, but space will stretch faster than gravity can cross it. The pull that has directed our trajectory since before the Earth existed will fade, attenuated by expansion, diluted by distance, finally rendered negligible by the relentless growth of the void between us. We will forget, not consciously, but effectively, our instruments no longer able to detect the distant influence, our motion no longer bearing its signature. The Great Attractor will pass out of our observable universe, its light and gravity alike unable to bridge the gap that expansion has opened. This is the fate of all cosmic structure eventually. Not destruction, but isolation. Not annihilation, but irrelevance. The universe will not end in fire or ice, but in loneliness, each bound system drifting in its own private cosmos, the stars burning out one by one, the galaxies fading into darkness. The Great Attractor will suffer this fate along with everything else, its mass dispersed, its influence diminished, its very existence forgotten by whatever minds remain to remember. But that is billions upon billions of years distant. For now, for the span of human existence both past and future, the Great Attractor dominates our cosmic motion. For now, we fall toward it, and in that falling we're connected to something vastly larger than ourselves, a structure spanning 300 million light-years, a concentration of mass equivalent to millions of galaxies, a gravitational centre that shapes the motions of everything in our cosmic vicinity. We cannot see it directly, but we know it is there. We cannot reach it, but we are travelling toward it nonetheless. We cannot escape its influence, but we have learned to measure and understand it, transforming blind subjection into informed awareness. This is what science offers, not control over our circumstances, but comprehension of them. We cannot change our trajectory through the cosmos. We cannot redirect our fall toward different destinations. We cannot escape the gravitational basin into which we were born. But we can understand these things, can know them, can hold them in our minds alongside everything else we know about the universe. The Great Attractor becomes not merely a force acting upon us, but a fact we have discovered, a truth we have uncovered, a mystery we have at least partially penetrated. In understanding, there is a kind of freedom, not the freedom to act differently, but the freedom that comes from knowing why we act as we do. The darkness behind the Milky Way's disk remains. The zone of avoidance still blocks our view. The Great Attractor still hides, revealed only through its gravitational fingerprints on the galaxies we can observe. But the mystery has been illuminated, if not dispelled. Patient observation across decades, using instruments of increasing power and ingenuity, has brought the hidden attractor into focus. Its position is known within a few degrees. Its mass is estimated within a factor of 2 or 3. Its relationship to the larger structures of the cosmic web, the superclusters and filaments and voids that span the observable universe, is increasingly well understood. The complete picture remains elusive, as it always does, as it perhaps always will. But the outline is clear now, and the details are filling in. This is where the story ends for now. Not with a final answer, but with a deepening question, not with resolution, but with richer mystery. The Great Attractor exists. It pulls us toward it. We cannot see it, but we have learned to perceive it through other means. We will never reach it, but we are falling toward it nonetheless. And in that fall, that endless streaming motion across the cosmic deep, we have discovered truths about the universe that observation alone could never reveal. Gravity spoke, and we learned to listen. The darkness concealed, and we developed new ways of seeing. The universe remained stranger than we imagined, but we met that strangeness with curiosity rather than despair, with inquiry rather than resignation, with the peculiar human insistence that what is unknown need not remain forever unknowable. Somewhere in the direction of the Southern Cross, hidden behind the very stars that guided sailors across Earth's oceans, an immense concentration of matter waits. It has been waiting for billions of years, pulling galaxies toward it, shaping the cosmic web, directing flows that span distances greater than any human journey could conceive. It will wait for billions more, patient and persistent, its gravity reaching out across the void to touch everything within its immense sphere of influence. We are within that sphere. We have always been within it. We will remain within it until dark energy finally triumphs and the expansion of the universe tears us away. Until then, we fall. And in the falling, we have found meaning. Not the meaning of purpose or design, but the meaning of understanding, of connection, of participation in something far larger than ourselves. The Great Attractor does not care about us, does not know we exist, has no intentions or plans or goals. But we know about it. We have traced its influence across hundreds of millions of light years. We have weighed it from afar, mapped its position despite the obscuring dust, reconstructed its history from the motions of distant galaxies. In doing so, we have written ourselves into the cosmic story, not as central characters, but as observers, witnesses, chroniclers of forces that dwarf our comprehension but not our curiosity. The instruments continue their work, the surveys expand, the measurements grow more precise, the models improve, and slowly, carefully, persistently the darkness yields its secrets. The Great Attractor, once a complete mystery, is now a known unknown, a specific gap in our cosmic map rather than undiscovered territory. The difference matters immensely. What we know we do not know we can investigate. What we have identified as hidden we can seek to reveal. The mystery remains, but it is a bounded mystery now, a challenge rather than an abyss. We are still falling, as we have been for eons, as we will be for eons more. But now we know where and why and toward what. And in that knowledge, uncertain and incomplete as it remains, we have achieved something remarkable. A glimpse behind the curtain of dust and stars that hides one of the universe's grandest structures. A structure that has shaped our cosmic fate since before our galaxy existed. The Great Attractor hides no longer. Not entirely. Not forever. We have found it, named it, measured it, understood it as well as our instruments and our minds allow. And tomorrow, with better instruments and sharper minds, we will understand it better still. The flow continues. The galaxies stream. The universe unfolds its secrets to those patient enough to seek them. And we, small creatures on a small world in the outer reaches of an ordinary galaxy, falling endlessly toward a destination we cannot see and will never reach, have managed nonetheless to comprehend our trajectory, to trace our path through the cosmic deep, to know, actually know something of the immense gravitational architecture that guides our journey through the void. The darkness is vast, but it is not absolute. The mystery is deep, but it is not impenetrable. The fall is endless, but it carries us toward understanding as surely as it carries us toward the hidden heart of Laniakea. And so the work goes on, as it must, as it always has, because the universe is comprehensible to those who take the trouble to comprehend it, and we have taken that trouble and we will continue to take it until the last star fades and the darkness finally becomes complete.